You are looking at something that shouldn't exist, not because it's hidden, but because its light should have never reached us. For 13.5 billion years, these photons traveled across an expanding universe, stretching, fading, turning ancient, until they finally touched the mirrors of the James Webb Space Telescope. And what came back doesn't make sense. This object, MOM-Z14, appears too early, too formed, too impossible for the universe we think we understand. Some call it a cosmic miracle. Others see it as a warning, because if this is real, then something about our understanding of the universe is wrong. That tiny patch of sky contains 10,000 galaxies, every galaxy, billions of stars. Now close your eyes and try to remember the oldest thing you have ever seen. A crumbling cathedral, a fossil pressed into stone, a photograph of someone dead for a century. Whatever came to mind, set it aside. Because the oldest thing a human being has ever looked at is not in a museum. It is not buried underground. It is not preserved in glass. It is a smear of light so faint that even the most powerful telescope ever built nearly missed it. And it has been traveling toward us for 13.5 billion years. It is called MOM-Z14, the Mother of Miracles. That is not a poetic nickname invented after the fact. That is what the scientists who found it called it in the room on the night the data confirmed what they were seeing. And a cosmic miracle. A galaxy so distant, so ancient, so impossibly bright for something that should barely exist, that the researchers who confirmed it said they sat with the numbers for a long time before they believed them. Its light left home 280 million years after the Big Bang. To understand what that means, you have to understand how far back that is. The universe is approximately 13.8 billion years old. The light from MOM-Z14 left its source when the universe was roughly 2% of its current age. Not the early universe in the loose, conversational sense. The genuine infancy of existence. The epoch when the first stars were still learning how to burn. When the raw material of everything we would one day call reality was still mostly darkness and cooling hydrogen. That is when this galaxy was already blazing. Already forming stars at a ferocious rate. Already doing things our models of cosmic evolution said it had no business doing yet. And there is more. When astronomers analyzed the chemical fingerprint of MOM-Z14, they found something that stopped the analysis cold. The ratio of nitrogen to carbon inside this galaxy matches something we have seen before, but never expected to see here. It matches the chemical signature of globular clusters, the oldest stellar structures in the observable universe, the ancient spherical cities of stars that orbit the Milky Way like fossils of a universe that came before. We had always assumed globular clusters took billions of years to form. We had written their origins into our models of cosmic history at a comfortable, reasonable distance from the beginning of time. MOM-Z14 suggests we were wrong. If its chemistry is correct, if the measurements hold, then globular cluster formation did not begin billions of years after the Big Bang. It began almost immediately, in the first few 100 million years, before the universe was even transparent. The timeline we built so carefully, the one calibrated and confirmed across decades of observation, has a crack running through its center. And that crack is getting wider every time JWST sends data home. This is not the story of one galaxy. That is the thing you need to understand before we go any further. One anomaly is interesting. One anomaly gets published, scrutinized, maybe revised. But what JWST has been finding since it opened its golden mirror to the sky in 2022 is not one anomaly. It is a pattern. A growing, systematic, relentless pattern of galaxies that should not exist. Too massive, too bright, too chemically mature, too organized, too early. Every time the telescope looks deeper, the universe answers with something that our best models said was not supposed to be there. Prepare yourselves. We begin. Light travels at 186,000 miles per second. That number is so familiar, it has lost its ability to astonish. We say it the way we say the boiling point of water. A fact, a given, a number to be memorized and moved past. Stop and feel it. 186,000 miles per second. The circumference of Earth is about 24,900 miles. Light could circle this entire planet more than 7 times in a single second. A passenger jet traveling from New York to London takes about 7 hours. Light covers that same distance in roughly 17 milliseconds, 17 thousandths of a second. You cannot blink faster than light crosses an ocean. And yet the universe is so incomprehensibly vast that even at 186,000 miles per second, light takes time. A lot of time. Embarrassing amounts of time. The light reaching your eyes from the moon tonight left its source 1.3 seconds ago. The light from the sun left 8 minutes ago. The light from the nearest star beyond our sun, Proxima Centauri, began its crossing 4.24 years ago. That light is a time capsule. You are not seeing Proxima Centauri as it is tonight. You are seeing Proxima Centauri as it was in the spring of 2021. Go further. The Andromeda Galaxy hangs in the northern sky as a faint smear visible to the naked eye on clear nights. The light that falls on your eyes from that smear left its source 2.5 million years ago, while that light was crossing the void between galaxies. Our early humans were learning to chip stone into tools on the African savanna. They had no concept of galaxies, no concept of the void they lived inside, no concept of the 2.5 million year journey that ancient light was making toward eyes that did not yet exist. That light did not wait for us. It simply traveled. Now consider MOM Z14. The light James Webb captured from MOM Z14 traveled for 13.5 billion years before it arrived. When that light left its source, our solar system did not exist. Earth did not exist. The atoms in every human body had not yet been forged inside any star. The Milky Way was still assembling its first structures in the primordial dark. Everything that has ever happened in the history of this planet, the formation of the oceans, the emergence of life, the Cambrian explosion, the age of dinosaurs, and with the rise of primates, every civilization, every war, every discovery, every person who ever lived, and every person alive today, all of it unfolded while that single packet of light was crossing the universe to get here. The word telescope, used to mean a device for seeing things far away, it has come to mean something else entirely. Every image James Webb captures is an archaeological excavation through stacked layers of cosmic time. The closer objects in any deep field image are recent history. The faint, barely resolved smudges near the edge of detection are the most ancient past that photons can deliver. When JWST pointed at the region of sky where MOMZ-14 was hiding, it was doing something that has no real analogy in human experience. It was receiving a message sent before the solar system existed, before Earth existed, and before the chemistry that would eventually produce every living thing on this planet had been assembled inside any stellar furnace anywhere in the cosmos. That is what redshift means in practice. Not a number in a catalog. A biography of light. When an object moves away from an observer, the wavelengths of its light get stretched. The faster it recedes, the more they stretch. The more they stretch, the redder the light becomes. In an expanding universe, distant galaxies are not just moving away from us. Space itself is stretching between us and them, carrying their light along with it. Galaxies at enormous distances are receding so fast that their light, originally emitted as ultraviolet radiation, arrives at our telescopes as infrared, shifted far beyond the range of human eyes. The James Webb Space Telescope was built specifically for infrared. It was designed from the beginning to catch exactly this kind of ancient, stretched, red-shifted light. MOM Z14 has a redshift of 14.44. In practical terms, that means the light James Webb measured had its wavelength stretched by a factor of more than 15 since it was emitted. What left MOM Z14 as energetic ultraviolet light arrived at Webb's mirror as deep infrared, invisible to any human eye, invisible to any instrument built before this one. The universe had been holding this message for 13.5 billion years, waiting for something sensitive enough to read it. To understand why MOM Z14 is extraordinary, you need to understand what the universe was doing at the time it existed. You need to know the landscape. The Big Bang did not produce stars. It produced heat and radiation, and within the first few minutes, the lightest elements, hydrogen, helium, and trace amounts of lithium. For hundreds of thousands of years after the initial explosion, the universe was a hot plasma, a fog so dense that light could not travel freely through it. Photons scattered off charged particles constantly, ricocheting in every direction, unable to make any progress. The universe was opaque. Then, approximately 380,000 years after the Big Bang, something changed. The universe cooled enough that electrons and protons could combine into neutral hydrogen atoms. This process, called recombination, cleared the fog almost instantly on cosmic timescales. For the first time, light could travel freely through space. The universe became transparent. But it was dark. There were no stars yet, no galaxies, and no points of light anywhere in the observable universe. Just vast, slowly cooling clouds of neutral hydrogen drifting in the expanding dark. Cosmologists call this period the Cosmic Dark Ages. It is perhaps the most alien epoch in the history of the observable universe. A universe full of matter, full of potential, but completely lightless. Then gravity did what gravity always does. Given enough time, even small density variations are amplified. Regions that were slightly denser than their surroundings pulled more gas toward them. They grew denser still. They pulled harder. Eventually, pockets of gas grew dense enough and hot enough that nuclear fusion ignited. The first stars were born. The first stars were nothing like the stars we know. Formed from pure hydrogen and helium with no heavier elements at all, yet they were almost certainly enormous by today's standards. Some models suggest they were hundreds of times the mass of our own sun. They burned hot and fast, lived short lives measured in millions rather than billions of years, and when they died, they seeded the surrounding gas with the first heavy elements the universe had ever seen: carbon, oxygen, nitrogen, silicon, iron, the raw materials of planets and chemistry, and eventually life. Those first stars also did something else. Their ultraviolet radiation was powerful enough to strip electrons from the surrounding neutral hydrogen, ionizing it, making it transparent to the radiation passing through. This process, called rionization, spread outward from early star-forming regions like bubbles of clarity in a sea of fog, over hundreds of millions of years. Those bubbles grew and merged until eventually the entire universe had been reionized. The cosmic dark ages ended. The universe became transparent not just to the faint background glow of the Big Bang, but to the light of stars and galaxies and everything that came after. The transition from the first stars igniting to the complete rionization of the universe defines the cosmic dawn. Astronomers have been trying to observe it for decades, to see the first galaxies forming in that earliest transparent epoch, to catch the universe in the act of producing its first organized structures. Before JWST, the record for the most distant confirmed galaxy stood at a redshift of just over 11, a galaxy that existed approximately 420 million years after the Big Bang. That was already extraordinary, already a challenge to explain. And then JWST launched in December 2021, opened its mirror in the cold of deep space beyond the orbit of the moon, and began to look. Within its first year, it had shattered every previous distance record. Within 2 years, it had found galaxies so early, so massive, so chemically evolved, that the community of cosmologists began using a phrase that had rarely been uttered in public before. The standard model of galaxy formation might be wrong. Not wrong in a small way. Not wrong in a way that requires modest adjustment. Wrong in a way that might require rebuilding entire sections of the theoretical framework from scratch. For a brief window in 2024, the title of most distant confirmed galaxy in the observable universe belonged to a galaxy discovered by JWST called JADES-GS-Z14-0. Yet scientists who spent careers building toward such a moment described the confirmation of its redshift as a night they would not forget. Its redshift was measured at Z equals 14.18. Its light had been traveling since the universe was approximately 290 million years old. 290 million years after the Big Bang. That sentence deserves a pause. Our solar system formed about 4.6 billion years ago. That means JWST-GS-Z14-0 existed roughly 4.3 billion years before our sun was born, before the cloud of gas and dust that would become Earth had even begun to condense, before a single grain of the rock beneath your feet had been synthesized inside any star. The discovery of JWST-GS-Z14-0 was not just a distance record, it was a scientific crisis in slow motion. The galaxy was too large, too bright, too chemically enriched. Everything about it suggested a longer history than 290 million years could explain. The stellar populations inside it were too evolved, the chemical abundances were too mature. Something had been happening in the early universe at a pace our models of galaxy formation had simply not accounted for. The astrophysics community was still processing that finding when, in April 2025, a team at MIT's Kavli Institute pointed JWST at something they had found in archival data, an object that appeared in infrared but vanished entirely at shorter wavelengths. That dropout pattern is the fingerprint of extreme distance. Every galaxy beyond a certain redshift wears it. Short wavelength light, ultraviolet and blue, gets absorbed by the neutral hydrogen surrounding the galaxy and along the line of sight before it can escape to travel across 13 billion years of universe to reach us. The galaxy goes dark in the blue. It blazes in the red. This object was blazing. The team used JWST's near-infrared spectrograph, an instrument capable of dispersing an object's light into its component wavelengths with extraordinary precision to measure the redshift directly. The spectroscopic confirmation came back, Z equals 14.44. The previous record had stood for less than a year. MOMZ-14, the mother of miracles. Its light had been traveling since the universe was 280 million years old, 10 million years earlier than the previous record holder. In cosmological terms, that is a significant reach backward into a period when the universe was doing things we do not fully understand. The team did not immediately shout the result from every platform available to them. They sat with it. They checked it again. They ran alternative interpretations through every analytical pipeline they had. Could this be a misidentification? Could the spectroscopic signature be mimicked by something closer and more mundane? Every test came back with the same answer. The redshift was real. The distance was real. MOMZ-14 existed 280 million years after the Big Bang. Peter Van Dokkum, professor of astronomy and physics at Yale, who contributed to the team's analysis, gave an interview after the confirmation and searched for a comparison that could make the timescale tangible. And he landed on one that had been circulating among cosmologists. Sharks have been swimming in Earth's oceans for longer than the age of this galaxy, at the time its light was emitted. Ocean predators that predate every major mass extinction in Earth's history. Animals that watched the dinosaurs rise and fall and kept swimming. Their lineage represents a longer continuous thread of survival than the entire lifespan of MOMZ-14 at the moment James Webb photographed it. That comparison lands differently than most astronomical metaphors. It places deep time inside something living and breathing and present. You have seen a shark. You know what one looks like. You know they are ancient. And yet the age of sharks is a footnote compared to how early in the universe MOMZ-14 existed. Van Dokkum added something else. Something that should stop you in your tracks if you let it. James Webb, he said, was not supposed to find anything this early. Not yet. Not at this point in the mission. The discovery pipeline was built around conservative expectations about the scarcity of galaxies at extreme distances. The models said the universe at 280 million years old would produce at most a handful of faint, primitive structures barely organized enough to call galaxies, smudges of star formation in the dark, proto-galactic wisps, MOMZ-14 is not a wisp. MOMZ-14 is small. In absolute terms, its diameter is approximately 240 light-years. That sounds large until you compare it to the Milky Way, which spans roughly 100,000 light-years. MOMZ-14 could fit inside our galaxy 400 times over with room to spare. If the Milky Way were the size of a full football pitch, MOMZ-14 would be a patch of grass roughly 2 feet wide. But do not let the size deceive you. This object is not faint, it is blazing. For its mass and size, MOMZ-14 is producing light at a rate that our best models of early galaxy formation cannot explain. Stars are forming inside it at a furious pace, converting raw gas into stellar material at an efficiency that should not be possible given how recently the universe became transparent and how little time the raw material of galaxies had to assemble. When you run the numbers, when you take the luminosity of MOMZ-14 and work backward to ask what star formation rate is required to produce that much light, you arrive at a number that sits well outside the range any standard model predicts. The standard model of galaxy formation, built over decades of careful observation and hundreds of thousands of hours of computational simulation, makes specific predictions about what galaxies should look like at different epochs. At Z equals 14.44, at 280 million years after the Big Bang, the model predicts something small, faint, chemically primitive, and barely organized. The first tentative structures of what will eventually become galaxies after another billion years of assembly. MOMZ-14 is not that. It is already luminous beyond what the model allows, already converting gas into stars at a rate that, according to the models, requires conditions that should not yet exist. Something accelerated this galaxy. Something allowed it to grow and burn with a ferocity that the standard timeline has no mechanism to produce. There are several proposed explanations, and none of them are fully satisfying on their own. The first involves the physics of star formation in metal-free gas. In today's universe, star formation is a self-limiting process. Massive stars blast out radiation that heats and disrupts the surrounding gas, slowing the formation of new stars. Supernova explosions shock surrounding material and push it away from regions where new stellar formation could occur. This feedback loop caps star formation efficiency in modern galaxies at somewhere between 1 and 5% of available gas. The theoretical maximum under the most extreme modeled conditions is about 10 to 20%. In the very early universe, the first galaxies formed from gas with almost no heavy elements. Metal-free gas cools and fragments differently. Some theoretical models suggest that in the first galaxies, before the first generation of supernovae could propagate their disruptive shockwaves through the host galaxy, star formation could proceed at efficiencies far higher than anything seen in the modern universe. The feedback loop existed in principle, but had not yet had time to engage. A brief window of extraordinary stellar productivity, front-loaded into the first few 100 million years. This is called feedback-free star formation. It is a real theoretical framework with serious researchers behind it. It can, in principle, explain galaxies that are brighter than the standard model predicts. The question is whether it can explain MOMZ-14 specifically. The numbers are right at the edge of what even the most optimistic versions of this theory allow. The second explanation involves the nature of the stars themselves. And the very first generation of stars, formed from pure hydrogen and helium with no contaminating metals, may have been far more massive than typical stars today. Models of population 3 stars, as they are called, suggest masses hundreds of times greater than our Sun. More massive stars produce more ultraviolet light per unit of mass. If MOMZ-14's luminosity is partially inflated by a stellar population dominated by these enormous first-generation objects, the galaxy might appear brighter than its actual mass would justify. Webb might be seeing an optical illusion of sorts. Not a more massive galaxy, but a galaxy whose stars are simply more wasteful with their light. The third explanation is the most uncomfortable one. The chemical measurements. When you point a spectrograph at a distant galaxy, you are not just measuring its distance. You are dissecting its light into individual wavelengths, each one carrying the signature of specific atoms. Hydrogen absorbs at certain wavelengths, carbon at others, oxygen at others still, nitrogen at others. The relative brightness of these absorption and emission features tells you not just what elements are present, but in what proportions? It gives you the chemical history of the galaxy in a single measurement. What the team found in MOMZ-14's spectrum was unexpected. The ratio of nitrogen to carbon inside this galaxy is high, unusually high, and that ratio pattern is recognizable. It matches globular clusters. Globular clusters are among the oldest stellar structures in the observable universe. They are dense, spherical collections of stars, some containing millions of individual suns packed into a volume only a few hundred light-years across. They orbit the Milky Way and other galaxies as ancient relics. Many of the globular clusters visible in our own galaxy today are between 10 and 13 billion years old. They have been orbiting here since before Earth existed, since before our sun ignited. For decades, astronomers assumed globular clusters formed in the first few billion years of cosmic history. The details of when and how were uncertain, but the general assumption was that globular cluster formation was a process that played out over an extended period, requiring the universe to build up sufficient stellar mass and chemical complexity before these dense stellar cities could coalesce. MOMZ-14's nitrogen to carbon ratio suggests something different. If the chemical signature in MOMZ-14 genuinely matches globular cluster precursors, if the object we are seeing at 280 million years post-Big Bang is already developing the chemistry associated with these ancient stellar systems, then globular cluster formation did not wait billions of years. It began almost immediately, within the first few 100 million years, in the epoch that was supposed to be too early, too primitive, too chemically barren for anything as organized as a globular cluster precursor to exist. This is not a small revision to the timeline. This is a rewrite. The globular clusters orbiting the Milky Way today are among the most studied objects in astronomy. We have spent decades analyzing their chemistry, their ages, their stellar populations, their formation histories. If those ancient objects, which we can examine in extraordinary detail with ground-based and space-based telescopes, were already forming their precursor chemistry less than 300 million years after the Big Bang, we have fundamentally misunderstood when and how the first large-scale stellar structures assembled. Rebecca Bowler at Oxford University, who has worked on early galaxy formation, noted in interviews following the MOMZ-14 announcement that the nitrogen enrichment was one of the most striking aspects of the discovery. Nitrogen at this level requires multiple generations of stellar evolution to produce in standard models. It requires stars to form, burn through their fuel, die in supernovae, scatter their heavy elements into the surrounding gas, and then a new generation of stars to form from that enriched material. But the fact that MOMZ-14 at 280 million years old already shows this enrichment suggests that stellar generations were cycling faster than we thought. That the first stars were forming, dying, and enriching the surrounding gas at a pace we had not built into our models. There is a phrase that cosmologist Peter Van Dokkum used in a subsequent discussion. He said the chemical signature was like finding an adolescent where you only expected to see babies. The galaxy is not just old for its time. It is chemically mature for its time. And chemical maturity requires generations. Generations require time. The time available between the Big Bang and MOMZ-14's observation was 280 million years. That is enough time for stellar generations to cycle, but only barely, and only under conditions of extraordinary efficiency that the standard model has no mechanism to produce at that epoch. The nitrogen-to-carbon ratio in MOMZ-14 is not a minor footnote. It is potentially the most diagnostically important measurement in the entire observation. The distance record will be broken again. The luminosity anomaly might be explained by feedback-free star formation or population 3 stellar populations. But the chemical signature is harder to hand-wave away. Chemistry requires history. History requires time. And the time available at Z equals 14.44 is razor-thin. The James Webb Space Telescope did not have to find MOMZ-14. That is the detail that most people miss in the coverage of the discovery. JWST was designed to find galaxies at extreme redshifts. Now, its infrared sensitivity was calibrated specifically to detect the stretched, red-shifted light of the earliest structures in the observable universe. The engineering specifications were set by predictions from the standard cosmological model about what the early universe contained and how bright those early structures would be. The telescope was built to find what the model predicted. What the model predicted were faint, sparse, primitive structures. A handful of detections at Z greater than 12 over the full mission lifetime. A trickle of data points from the cosmic dawn that would, over years of patient observation, build a statistical picture of how the first galaxies formed. What JWST has actually found, 3 years into science operations, is a flood, not just MOMZ14, not just JADES-GS-Z14-0. And since the telescope began returning science data in the summer of 2022, more than 100 confirmed galaxies have been catalogued from the first 400 million years after the Big Bang. More than 100. The model predicted a handful. The universe delivered a crowd. And not a crowd of faint primitive smudges, but a crowd of objects that are, in many cases, larger, brighter, and more chemically evolved than any reasonable version of the standard model could explain. Michael Boylan Colchin of the University of Texas at Austin ran the numbers carefully and published the result. Some of the massive galaxies JWST found at the highest redshifts require star formation efficiencies of 50% or higher to have assembled their stellar mass in the available time, in the present-day universe. And the fraction of available gas that actually converts into stars typically sits between 1 and 5%. The standard model predicts a theoretical maximum of 10 to 20% under the most favorable conditions ever modeled. 50% requires conditions the existing framework has no mechanism to produce. And some galaxies appear to need efficiencies approaching 100%. Every available atom of gas converted into stars almost instantaneously on cosmic timescales, with no waste, no suppression, no physical process slowing the conversion down. The known physics of star formation should make that impossible. Supernovae alone should disrupt a galaxy's gas supply long before efficiency approaches those levels. When a massive star reaches the end of its life and explodes, and the energy released is enough to heat and expel enormous quantities of surrounding gas, shutting off the fuel supply that future star formation depends on. This self-regulation mechanism is built into every model of galaxy formation at every epoch. It is not an optional feature. It is a fundamental physical process that operates everywhere we can observe it in the modern universe. And yet, the early universe appears to have bypassed it somehow. Van Dokkum's statement that Webb was not supposed to find anything this early deserves its full context. The telescope was not underpowered for the task. It was not pointing in the wrong direction. The discovery of MOMZ14 was not an accident of circumstance. It was found in data that the instrument collected while doing exactly what it was designed to do. The problem is not with the telescope. The problem is with the expectation. The model said the universe at Z equals 14.44 should contain almost nothing. The universe at Z equals 14.44 contains MOMZ14. That mismatch between prediction and observation is not a failure of instrumentation. It is a signal, one of the clearest signals in modern astrophysics. Something is wrong with the standard picture of early cosmic structure formation, and whatever that something is, it has been operating since the first few 100 million years of existence, producing galaxies bigger and brighter and more chemically evolved than the theory allowed. The scientific question is not whether the standard model needs revision. It clearly does. The question is how much revision. And the answer to that question is still being contested in seminars around the world. The story of how humanity learned to look at objects this distant begins with a decision that seemed almost reckless when it was made. In December 1995, astronomers pointed the Hubble Space Telescope at a patch of sky in the constellation Ursa Major that contained no bright stars, no known galaxies, no catalogued objects of any kind, just an empty-looking rectangle of darkness. They kept it pointed there for 10 consecutive days. What came back from that observation changed everything. Within that patch of sky so small that you could cover it completely by holding a grain of sand at arm's length, researchers counted approximately 3,000 galaxies, each one containing hundreds of billions of stars, each one there, waiting in a direction everyone had assumed was empty. The original Hubble Deep Field covered about a millionth of the total sky. Scientists repeated the observation at higher sensitivity in later years in a project known as the Hubble Ultra Deep Field, and the count in that tiny window climbed to approximately 10,000 galaxies. Then came the arithmetic that genuinely disturbed people. The full sky contains room for about 13 million patches that size. If each patch holds roughly 10,000 galaxies, then a rough extrapolation puts the total galaxy count somewhere around 100 to 200 billion. That number sat in textbooks for 2 decades. It was, as later work revealed, a dramatic undercount. St. Christopher Consolis at the University of Nottingham spent years building 3-dimensional models of how galaxy populations change through cosmic time and recognized that the straightforward extrapolation was missing something essential. The faintest, most distant galaxies, the small, numerous objects that dominated the first billion years of cosmic history, were simply below the detection threshold of every telescope that had existed. They were real. They were producing light. That light crossed billions of light years to reach the vicinity of Earth and then fell short of triggering any detector. They had never been counted. When Consolis's team published their revised calculation, the corrected total was not 200 billion. It was 2 trillion, 10 times higher than the previous estimate. While more than 90% of all galaxies in the observable universe had been invisible to human instruments and therefore absent from every count ever made. 2 trillion galaxies. Consolis offered a comparison to give the number a human scale. 2 trillion is roughly the number of seconds in 1,000 average human lifetimes. Counting at 1 galaxy per second without pause would take 63,000 years to reach 2 trillion. Human civilization, including all of recorded history from the earliest writing to the present day, is approximately 10,000 years old. The count would not be finished in the entire span of human civilization so far. JWST was designed and justified in part by the need to observe this invisible majority. The galaxy is too faint and too distant for Hubble to detect. The universe's hidden population, existing at redshifts beyond Hubble's reach, waiting for an instrument with infrared sensitivity powerful enough to capture their stretched light. When JWST found MOMZ-14 in data collected by the Cosmos Web Survey, one of the largest JWST programs ever executed, it confirmed something Consolis had predicted years earlier. The faint, early galaxy population is not just present, it is massive, numerous, bright, chemically evolved, and it is challenging everything we thought we knew about when organized cosmic structure began. The search took this long because the light from these objects is genuinely difficult to detect, not impossible, not beyond the reach of physics, but exacting in its demands. It requires a telescope cold enough to minimize its own infrared radiation, large enough to collect enough photons from objects emitting only fractions of what modern galaxies produce, stable enough to make multi-hour exposures without drift, and positioned far enough from Earth to avoid the infrared glow of our own planet's warmth contaminating every observation. JWST satisfies all of those requirements. It orbits the L2 Lagrange point 1.5 million kilometers from Earth, kept in permanent shade by a tennis court-sized sun shield that keeps its mirror and detectors cooled to minus 233 degrees Celsius. It has been operating there since January 2022, and every month since then, it has been finding things that the people who built it did not predict. MOMZ-14 was not found by pointing JWST at a blank patch of sky and hoping. It was found inside an enormous mosaic of the universe built by one of the most ambitious survey programs in the history of space astronomy. The Cosmos Web Survey was the product of years of planning, argument, and competition for observing time on the most expensive scientific instrument ever launched. Time on JWST is measured in hours, and those hours are genuinely finite. Every hour spent on one target is an hour not spent on something else. The teams making the case for a massive wide-field survey had to convince the scientific community that covering a large area of sky in detail was worth the cost of everything they would not be observing. They were granted 255 hours. The co-principal investigators, Jehan Kartaltepe of the Rochester Institute of Technology and Caitlin Casey of the University of California, Santa Barbara, had led a team that mapped an area of sky roughly 3 times the size of a full moon. They used JWST's near-infrared camera to cover 0.54 square degrees of the cosmos field, a patch of sky in the constellation Sextans that had been studied by dozens of telescopes over the previous 2 decades, and was chosen because so much prior data already existed to compare against. The technique required stitching together more than 10,000 individual images into a single coherent mosaic. The process took years of calibration, testing, and refinement, even before the telescope launched. The data arrived in waves, each requiring enormous computational effort to process and merge with what came before. In June 2025, the team released the full Cosmos Webb 2025 catalog. It contained nearly 800,000 galaxies, each detected across 37 photometric bands, meaning each galaxy was measured at 37 different wavelengths of light. The combination of those measurements allowed researchers to estimate not just where each galaxy was in the sky, but how far away it was, how old its stars were, how fast it was forming new ones, and how much dust it contained. 800,000 galaxies in a patch of sky, 3 times the size of the full moon. If you printed the Cosmos Webb mosaic at the density of a standard newspaper, the image would stretch across a surface the size of a full football pitch. Every smear, every blur, every barely resolved speck in that image would be an entire galaxy. The survey spans cosmic history from objects relatively nearby to galaxies that existed when the universe was barely 7% of its current age. MOMZ14 was in that dataset, hiding in the mosaic, appearing bright in infrared wavelengths, vanishing entirely at shorter wavelengths. The dropout pattern was there in the data, waiting for someone to look. The MIT Kavli team was looking. They found the candidate object during a systematic sweep through the Cosmos Webb catalog, searching specifically for objects with the photometric signatures of extreme redshift. The dropout pattern, the infrared brightness combined with complete absence at shorter wavelengths, flagged MOMZ14 as a priority target for spectroscopic follow-up. That follow-up, conducted in April 2025 using JWST's near-infrared spectrograph, confirmed the redshift at Z equals 14.44. The discovery illustrates something important about how modern astronomy works. MOMZ14 was not discovered by building a dedicated telescope and aiming it at one object for months. And it was discovered because a massive survey program collected data across an enormous area of sky. That data was processed into a public catalog, and a team with the right analytical approach searched that catalog systematically. The telescope was a tool. The survey was infrastructure. The discovery was the product of human pattern recognition applied to an enormous data set. Maximilian Franco of the University of Paris-Saclay, who led the imaging pipeline for Cosmos Webb, described the experience of working with the data. Objects that had been entirely invisible at every other wavelength were emerging in JWST's infrared sensitivity. Galaxies that had left no trace in decades of prior surveys of the same field were suddenly there, resolving into brightness on the screens. Each one a message from deep time that no previous instrument had been sensitive enough to receive. The scale of the catalog is difficult to hold in the mind all at once. But every data point in it is a real object, every smudge and blur is a real galaxy containing hundreds of billions of real stars. And somewhere in that enormous mosaic, hiding in the infrared, was MOMZ14. The lambda cold dark matter model, usually shortened to lambda CDM, is one of the most successful scientific theories ever constructed. It describes how a nearly uniform universe emerged from the Big Bang, how tiny quantum fluctuations in density grew into seeds of structure, how gravity amplified those seeds into clumps of dark matter, how gas fell into those clumps and fragmented into the first stars and galaxies, and how the large-scale structure we observe today, the cosmic web of filaments, clusters, and voids, assembled over 13.8 billion years. The model is supported by decades of observation across every wavelength of the electromagnetic spectrum. It makes accurate predictions about the temperature fluctuations in the cosmic microwave background, the oldest light in the universe. It correctly predicts the large-scale distribution of galaxies in the nearby universe. It accurately describes the expansion history of the universe. including the accelerating expansion driven by dark energy. In its domain, lambda CDM is extraordinarily precise. JWST has spent 3 years finding things it says should not exist. The problem began accumulating before Imam Z14. As the telescope turned toward deep fields and gravitational lenses and began cataloging galaxies at extreme distances, a pattern emerged. That the galaxies being found were too massive, too bright, too chemically evolved. They contained too many stars for their age, too much enrichment, too much organized structure. At every distance where the model made confident predictions about what should be there, JWST kept finding something more. The problem has multiple dimensions, and each one points to the same underlying inadequacy. The first dimension is mass. At redshifts greater than 10, lambda CDM predicts that galaxies should be small and low mass. The dark matter halos they inhabit at that epoch are predicted to be modest. The amount of time available for gas to fall in and form stars is limited, and the feedback processes that quench star formation in massive galaxies should not yet have created any very large systems. But some of the galaxies JWST has found in the first billion years are massive. Their stellar masses, inferred from their luminosities and colors, place them in a category that the standard model reserves for objects that should take much longer to build. The second dimension is brightness. For a given stellar mass, early galaxies in JWST's data are simply brighter than lambda CDM predicts. This could be explained in part by population 3 stellar populations, those hypothetical first-generation massive stars that produce more ultraviolet light per unit mass than modern stars. But the discrepancy in brightness is large enough that stellar populations alone cannot fully account for it in all cases. The third dimension is chemistry. This is where MOM Z14's nitrogen to carbon ratio enters the picture as part of a larger pattern. And multiple early galaxies found by JWST show chemical abundances that imply a longer history of stellar generations than the available time allows under standard assumptions. Heavy elements require stars to form, live, and die. Nitrogen specifically, in the abundance ratios seen in MOMZ14 and some other early galaxies, requires multiple cycles of stellar enrichment. The timeline is tight. It may be too tight. The fourth dimension is structure. Early galaxies in the standard model should be irregular, clumpy, disorganized. They are at the beginning of their assembly, building up mass from accreting gas and merging with smaller objects. What JWST has found in some cases is structure. Disk galaxies. Galaxies with organized rotation, galaxies with central bulges, morphological features that the standard model reserves for objects billions of years older than what JWST is observing. None of these dimensions is independently fatal to lambda CDM. Each one can be addressed with modifications to assumptions about star formation efficiency, stellar populations, feedback mechanisms, or dust. The theoretical community has been creative and productive in generating explanations. The problem is that the explanations required are not small adjustments. They require assumptions that push the boundaries of what the physics allows, and they need to be invoked simultaneously across multiple independent observational lines. When a theory requires multiple independent simultaneous adjustments, all pointing in the same direction, each one straining the boundaries of physical plausibility, the theory is telling you something. It is telling you that whatever you are adjusting for is real. Something is happening in the early universe that the standard model failed to predict. And the convergence of evidence from mass, brightness, chemistry, and structure in object after object across multiple independent surveys makes that conclusion increasingly difficult to dismiss. Science advances by subjecting its most dramatic claims to relentless pressure until only the ones that survive remain standing. The impossible galaxies are no exception, and the scrutiny they have received over 3 years has already revised some of the most extreme initial announcements downward. Most cosmologists working in this field do not believe the standard model is broken. They believe it is under stress. No, they believe our understanding of early star formation physics is incomplete. They also believe, based on years of experience with JWST data, that some fraction of the most alarming early claims will prove to have been overstated. The revision process has already begun. In the first 2 years of JWST operations, several galaxies announced with great fanfare as extraordinary distance records were later found to have been misidentified. The technique used to estimate galaxy distances from imaging data alone, called photometric redshift modeling, works by matching the brightness of a galaxy across multiple wavelengths to a library of theoretical templates. It is powerful and often accurate. It is also fallible in ways that matter enormously at extreme distances. A galaxy at a relatively modest distance that happens to be very red can mimic the dropout signature of an extremely distant galaxy in certain filter combinations. When spectroscopic follow-up, which directly measures the wavelengths of specific atomic emission lines and produces far more reliable distance estimates, was applied to some early high-profile candidates, the distances came back dramatically lower than the photometric estimates had suggested. This is the process working as designed. Photometric redshifts are screening tools. Spectroscopy is confirmation. The genuine distance records that remain standing, the ones that have survived spectroscopic verification, are locked in. The rest were drafts, not discoveries. This is why MOM Z14's spectroscopic confirmation matters so much. The Z equals 14.44 measurement is not a photometric estimate. It is a direct spectroscopic measurement of the galaxy's light dispersed into its component wavelengths. The Lyman break, the sharp cutoff in the galaxy's spectrum caused by hydrogen absorption, is precisely where it should be for a source at that distance. The emission features are where they should be. Multiple independent spectral features agree. The distance is real. The brightness problem also deserves honest assessment. Michael Boylan-Colchin's calculation that some early galaxies require star formation efficiencies above 50% is genuinely alarming, but some researchers have argued that the mass estimates underpinning those calculations may be systematically high. JWST's photometry is extraordinarily precise. But translating observed brightness into stellar mass requires assumptions about the stellar populations producing that brightness. If early galaxies are dominated by population 3 stars or by active galactic nuclei, massive black holes feeding on surrounding gas and adding their own light to the galaxy's total, the stellar mass estimates derived from standard photometric modeling could be overestimates. Some of the most extreme brightness anomalies have indeed been traced, upon follow-up, to AGN contamination. Active galactic nuclei can be extraordinarily luminous, bright enough that a single feeding black hole can outshine the entire stellar population of its host galaxy. If JWST is detecting AGN in some of these early objects and attributing all of that light to stars, the galaxy will appear more massive than it actually is. The deeper theoretical gap also deserves honest assessment. The discrepancy between what the standard model predicts and what JWST observes is real. It is statistically significant. It has persisted as better data arrived. But the gap could reflect the model's need for revision in its treatment of early star formation efficiency. It could reflect something more fundamental. It could also reflect selection effects, where JWST preferentially detects the rarest, brightest objects at extreme distances, while the more typical population at those redshifts remains too faint to catalog. One published review from early 2026 summarized the expert consensus plainly. It is too early to claim the standard model is broken. The observations are extraordinary. The discrepancies are genuine. The work is continuing. Drawing final conclusions now would be premature. Science under pressure can look like crisis and later reveal itself as growth. The history of cosmology is full of moments that seemed like they would require rebuilding the entire framework and turned out instead to require targeted modifications to specific assumptions. The standard model has survived challenges before. Whether it survives this one intact, or whether it requires something more fundamental to absorb what JWST is finding, is the most important open question in observational cosmology today. To understand why MOMZ14 challenges the standard model so directly, you need to understand the role dark matter plays in galaxy formation. Because dark matter is not a supporting character in this story, it is the protagonist. Dark matter emits nothing, reflects nothing, absorbs nothing. It interacts with ordinary matter only through gravity. There is no camera that can photograph it, no spectrograph that can fingerprint it, no wavelength of light it produces for any detector to catch. It has never been directly detected by any laboratory instrument on Earth despite decades of dedicated effort. We know it exists because of what it does to the things around it. Its gravitational pull on ordinary matter is so consistent, so precisely measured, and so systematically confirmed across so many independent lines of evidence that its existence is among the most secure conclusions in modern physics. And yet what it is remains entirely unknown. Dark matter makes up approximately 27% of the total energy content of the observable universe. Ordinary matter, everything you can see, touch, smell, everything made of atoms, accounts for only about 5%. The rest is dark energy, which is stranger still, a property of space itself that drives the universe's accelerating expansion. In the universe's total energy budget, all of the stars and galaxies and gas and dust and planets and people add up to roughly 1/20th of what is actually there. In the lambda CDM model, dark matter is the scaffold on which galaxies are built. The tiny quantum fluctuations in density present in the very early universe grew over hundreds of millions of years under the influence of gravity. Dark matter clumped first because it was not subject to the radiation pressure that kept ordinary matter from clumping too early. Dark matter halos formed first. Then ordinary gas fell into those halos, cooled and fragmented into stars. Yet then those stars organized into galaxies inside the halos. The model predicts that at Z equals 14.44, the dark matter halos available to host galaxies like MOMZ14 should be relatively small. The universe simply has not had enough time to grow the kind of massive dark matter concentration that a very bright, very massive galaxy requires. This is one of the fundamental predictions of lambda CDM's hierarchical structure formation scenario, which says that large structures form from the merger of smaller ones, and that the largest structures should therefore be absent at early times. MOMZ14 appears to require a dark matter halo more massive than hierarchical structure formation would predict for that epoch. There are several possible resolutions, none of them comfortable. The first is that we are overestimating the galaxy's mass. If the luminosity is partially due to AGN contamination or population 3 stellar populations, the true stellar mass is lower, which requires a less massive host halo, which is more consistent with standard predictions. This is the most conservative interpretation and the one most theorists prefer until it can be ruled out. The second is that dark matter halos at the highest density peaks in the early universe can grow faster than average models predict, due to rare statistical fluctuations in the initial conditions of the universe. The universe is large and varied. The spots we are observing are necessarily the most extreme overdensities of the early universe, because those are the places bright enough to detect. A galaxy like MOMZ14 might represent the tail of a statistical distribution, as an outlier rather than a representative example. The standard model can accommodate outliers without breaking. The third possibility is that dark matter itself behaves differently in the early universe than standard lambda CDM assumes. Some modifications to the dark matter model, such as warm dark matter or self-interacting dark matter, predict different halo mass distributions at early times. These modifications have been constrained by other observations, but not eliminated. If JWST continues to find galaxies that cannot be explained, even as outliers of the standard dark matter model, the properties of dark matter itself will come under scrutiny. In January 2026, a paper published in Nature Astronomy provided the sharpest map of dark matter ever produced from space-based observations. Diana Scognamiglio at NASA's Jet Propulsion Laboratory led the analysis, using approximately 250,000 background galaxies as probes of the dark matter distribution within the Cosmos Webb survey area. The map was twice as sharp as any previous space-based dark matter map at that scale, resolving structures that previous maps had merged into featureless blurs. when the comparison slide was shown at a collaboration meeting, placing the old Hubble-era dark matter map of the region next to the new JWST-era version, the room did something unusual for a scientific conference. People started clapping. The new map reveals the cosmic web in detail, the network of dark matter filaments connecting galaxy clusters, the voids between them, the invisible skeleton on which all of the visible universe is arranged. Nothing in that universe falls where it falls by accident. Every galaxy, every cluster, every thread of stars connecting one dense node to another occupies the position it does because dark matter pulled the surrounding gas there first, quietly and invisibly, over billions of years. MOM-Z14 sits at the end of one of those dark matter threads, at the beginning of cosmic time, burning with improbable brightness in a halo that should, according to standard models, not yet be massive enough to contain it. The nitrogen anomaly in MOM-Z14 is not the only chemical surprise that JWST has delivered from the early universe. It is part of a pattern that extends to other elements and other early galaxies, and together those anomalies paint a picture of an early universe that was chemically active far earlier than our models predicted. In early 2025, a result arrived that was published simultaneously by two independent research teams working from the same ALMA radio telescope data through completely separate methods. The confirmation from two groups at once made the result essentially impossible to dismiss. The measurement showed 10 times more oxygen than any reasonable model predicted a galaxy could have produced in the short time it had existed. The galaxy in question existed only 290 million years after the Big Bang, and it was already rich in oxygen. To understand why oxygen at this distance and depth is so extraordinary, you need to understand where oxygen comes from. The Big Bang produced hydrogen and helium almost exclusively. Every atom of oxygen in your body, in Earth's oceans, in the air you breathe, was made inside a star through nuclear fusion. When a massive star exhausts its fuel and explodes as a supernova, it scatters its freshly forged heavy elements back into the surrounding gas. The next generation of stars forms from that enriched material. That process takes time. Stars must be born. They must burn through their fuel, which takes millions to tens of millions of years even for the most massive ones. Then they must die and scatter their contents. Then the next generation must assemble from the enriched gas and ignite. For a galaxy that existed only 290 million years after the Big Bang to show 10 times more oxygen than expected, multiple complete cycles of stellar birth and death had already happened inside it. Multiple generations in 290 million years. Under conditions that the standard model of star formation says should have been far less efficient than what this measurement implies. Researchers describe the discovery as finding an adolescent where you would only expect babies. The second team's lead scientist said the evidence opened a new view on the first phases of galaxy evolution that nobody had been prepared for. The enrichment that took the Milky Way billions of years to accumulate had already happened, in a fraction of that time, inside this compact blazing structure. The ALMA measurement of the galaxy's distance achieved accuracy to within a fraction of a percent. That is the equivalent of measuring a distance of 1 kilometer and being accurate to within 5 centimeters at 13.5 billion light years with a radio telescope on the ground. The precision is real. The oxygen is real. What this forces onto the table is a problem far larger than one galaxy. If that ancient object was already chemically mature before the universe was 300 million years old, then the stars responsible for all that enrichment had to be forming, living, and dying in the first 200 million years, or less. The very first sliver of cosmic time. That pushes the opening act of stellar history far earlier than any model predicted. And that is when the crisis in cosmology stops being about individual galaxies and starts being about the entire framework. MOM-Z14's nitrogen anomaly fits into this same picture. 2 independent early galaxies, 2 independent chemical anomalies, both suggesting stellar generations that could not have cycled in the available time under standard assumptions, when both pointing toward the same conclusion. The early universe was forming stars more efficiently, living and dying faster, enriching surrounding gas more rapidly than anything built into the Standard Model. The oxygen finding and the nitrogen finding are not the same measurement. They are not the same galaxy. They came from different instruments, different teams, different analysis methods, different observational programs. And they agree. The early universe was chemically active on a timeline that the Standard Model says is impossible. That is not coincidence. That is signal. MOMZ-14 does not exist in isolation. It is one data point in an increasingly dense picture of what the early universe actually looked like. And that picture, assembled piece by piece from JWST observations over 3 years, shows an early cosmos that was not the empty, slowly assembling place of standard theory, but something more chaotic, more structured, more active. In June 2024, a paper appeared in the journal Nature, describing something that Angela Adamo, a researcher at Stockholm University, focused on how star clusters form and survive, described as a chain of small shocks arriving in rapid succession. Her team had targeted a gravitationally lensed galaxy sitting at a redshift of approximately 10.2, that places it 460 million years after the Big Bang. Inside the images, inside a region spanning less than 230 light-years, the team resolved 5 compact objects, 5 separate distinct concentrations of stars, each one spanning only about 3 light-years, each one packed with approximately 1 million stellar masses. Those 5 objects are called the cosmic gems arc. Their density is the number that most clearly communicates what makes them extraordinary. Star clusters in the nearby universe have stellar surface densities ranging from a few hundred to a few thousand times the mass of a typical star per square light-year. The cosmic gems clusters have stellar surface densities 1,000 times higher than the densest young star clusters observed anywhere in the local universe. They are packed to a degree that appears essentially nowhere in the galaxy population around us today. At those densities, something interesting happens. Massive stars crowd together closely enough that they interact gravitationally on timescales shorter than their individual stellar lifetimes. Runaway mergers become possible, where star after star falls into a growing central mass, accumulating until the product is something too massive to have formed through ordinary stellar evolution. That pathway is one proposed mechanism for creating intermediate mass black holes whose existence has long been suspected but whose formation process has never been directly observed. The cosmic gems clusters are younger than 50 million years old, measured from their stellar populations. Their metallicity is less than 1% of the metallicity of our own galaxy, consistent with objects forming in the earliest stages of chemical enrichment. Their masses and densities match what theorists have long predicted the ancestral globular clusters should look like before billions of years of dynamical evolution thinned and softened them into the ancient systems orbiting the Milky Way today. Larry Bradley of the Space Telescope Science Institute, who contributed to the analysis, noted that no other telescope could have made this discovery. That statement is accurate. Without JWST's infrared sensitivity and the cluster's gravitational magnification, these 5 objects would remain invisible. Embedded in data we would never know how to read. What the cosmic gems represent is the possibility of watching the birth of structures that have been with us in evolved form for the entire history of the galaxy. And they were born 460 million years after everything began. And now recall MOMZ-14 and its nitrogen to carbon ratio matching globular cluster signatures. Now recall that the cosmic gems are dense, ancient chemistry precursors to the globular clusters orbiting the Milky Way today. These are independent observations. Different telescopes, different teams, different targets, different analytical approaches. And they converge on the same conclusion. The building blocks of the oldest stellar structures in our own galaxy were forming within the first few 100 million years of cosmic history. The globular clusters we can examine in the Milky Way tonight, the ones we point backyard telescopes at on clear nights, are the descendants of objects that existed while MOMZ-14 was still blazing in the pre-dawn universe. The timeline is not what we thought. the cosmic vine adds another layer. In data from a survey called the CEERS field, a team at the Cosmic Dawn Center in Copenhagen found 20 galaxies with confirmed spectroscopic redshifts, all clustered between z equals 3.434 and z equals 3.45. That places them about 2 billion years after the Big Bang. Translated into physical distances, the structure those 20 galaxies trace is roughly 13 million light-years long and only about 650,000 light-years wide. The shape earned it its name. A long, narrow filament extending across the early universe, like a vine. The two most massive galaxies in the structure are each about 800 billion times the mass of our Sun. Enormous stellar masses for objects that existed only 2 billion years after the Big Bang. But mass was not what surprised the team most. What surprised them was that both galaxies had already stopped forming stars. In an environment teeming with activity, in a large-scale structure actively accumulating mass, surrounded by hundreds of star-forming galaxies, the two biggest members of the vine had gone quiet. Their stellar populations were old. Their star formation rates were effectively zero. Their shapes were dominated by central bulges rather than extended disks. They looked like the old red elliptical galaxies common in massive clusters in the nearby universe today. The nearby universe is 13.8 billion years old. These galaxies had reached that state in just 2 billion years. The standard model predicts this kind of quenching, this shutting down of star formation, but it predicts it happening later and more slowly. Yet the vine's massive members had accelerated through their entire active star-forming lives and arrived at quiescence billions of years ahead of the predicted schedule. And the protocluster JWST-Z14-1, discovered in early 2026 and described in a paper led by Akos Bogdan of the Center for Astrophysics at Harvard and Smithsonian, located 12.7 billion light-years away, existing when the universe was just barely over 1 billion years old. A structure containing at least 66 potential galaxy members. A total mass including the dark matter halo estimated at approximately 20 trillion times the mass of our Sun. The Chandra X-ray Observatory confirmed it was real and gravitationally bound by detecting the hot gas filling the space between its galaxies. Gas heated to millions of degrees by the cluster's gravitational assembly. Standard models predicted clusters of this mass should not begin appearing until the universe is significantly older. Bogdan described the finding as evidence that the universe was in a significant hurry to grow up. Each of these discoveries is extraordinary on its own. The cosmic gems, the cosmic vine, the protocluster, MOM-Z14. Taken together, they constitute something more than a collection of interesting objects. They constitute a challenge to the entire picture of when and how the organized structures of the universe assembled. MOM-Z14's nitrogen anomaly is one kind of surprise, the chemistry problem. But there is another pattern emerging from large-scale galaxy surveys that raises questions of a different order entirely. And it has nothing to do with how early galaxies formed. It has to do with which direction they spin. In a universe built on the principles of lambda CDM, galaxy spin should be random. There is no preferred direction in space. There is no preferred axis. The laws of physics are symmetric, operating identically in every orientation. When galaxies form from rotating gas clouds within dark matter halos, those halos have angular momentum acquired from the gravitational torques of surrounding structure, and that angular momentum can point in any direction. It should be roughly evenly distributed. Half the galaxies in any large survey should spin one way, half the other, with no systematic preference. A series of galaxy surveys has found evidence that challenges this expectation. When researchers analyzed the spiral arms of large samples of galaxies using the orientation of their trailing arms to identify their direction of rotation, they found a pattern, not a subtle one. The galaxies appear to rotate preferentially in one direction. The distribution is not 50-50. It is not random. There is a systematic skew that should not be there under the standard cosmological principle, which holds that the universe is isotropic, the same in all directions, and homogeneous, the same in all locations, on large scales. This observation is called cosmic anisotropy. It has been reported by multiple independent groups using different datasets and different methodologies. The results do not always agree in their details, but they converge on the same unsettling finding. The universe at large scales may have a preferred direction. A preferred direction requires an explanation. And the most straightforward explanation in terms of the physics is difficult to accommodate within standard cosmology. If there is a preferred axis, a direction that is somehow special, it could reflect conditions imposed on the observable universe at its formation. The most dramatic version of this idea connects back to the physics of black holes. When matter collapses under gravity to form a black hole, it creates an event horizon, a boundary beyond which nothing can escape, not even light. The region inside the event horizon is causally disconnected from the outside universe in a fundamental way. An external observer can never receive any signal from inside. The singularity at the center, if it exists, is shielded from all observation. But what happens inside the event horizon? Black hole cosmology, also called Schwarzschild cosmology in some formulations, proposes something radical. Our observable universe might actually be the interior of a black hole in a larger parent universe. The Big Bang, in this picture, was not an explosion in empty space, but rather the moment matter collapsed through an event horizon in that parent universe, creating a new space inside, a new universe, causally disconnected from its parent but real, expanding, capable of forming its own stars and galaxies and eventually its own black holes. Each of those black holes would be the doorway to yet another baby universe. If this picture is correct, the universe we inhabit was born with a preferred direction inherited from the rotation of the black hole that spawned it. Rotating black holes have angular momentum. A rotating black hole would pass that angular momentum to the universe born inside it, and that angular momentum would show up as a preferred direction in the distribution and rotation of the galaxies that form inside that universe. The galactic rotation asymmetry might be the imprint of our universe's birth. This is a speculative proposal. It is not part of the standard cosmological model. Many physicists are deeply skeptical of it for reasons ranging from the theoretical to the observational. But it is not scientifically empty. It makes specific predictions. It can in principle be tested. And the observations of galactic rotation asymmetry that have been accumulating over the past several years are at least consistent with it in a way that demands attention. And there is a connection to another feature of black holes that makes the proposal more mathematically sophisticated than it might initially appear. In extended theories of general relativity, including Einstein-Cartan relativity, there is a property called torsion. Standard general relativity treats spacetime as curved but not twisted. Einstein-Cartan extends this to allow for torsion, a twisting of spacetime that arises from the intrinsic spin of quantum particles. Some versions of Einstein-Cartan theory suggest that at the extreme densities inside a collapsing black hole, torsion creates a repulsive force that prevents the singularity from forming. Instead of collapsing to an infinitely small point, the core rebounds. It bounces. And that bouncing core expanding outward would look from inside exactly like a Big Bang. And the physicist proposing this picture compares the universe to a rebirth rather than an explosion. Not a singularity erupting from nothing, but a compressed core of matter from a previous universe, rebounding outward through a process of torsion-induced repulsion, expanding into a new space that is causally disconnected from its parent, but physically continuous in the sense that it inherits the angular momentum, the physical constants, and possibly the topological structure of the black hole from which it formed. If true, this picture has another implication that is philosophically startling. The fundamental constants of nature, the precise values of the gravitational constant, the speed of light, the masses of elementary particles, the strength of the electromagnetic force, all of the parameters that must be fine-tuned with extraordinary precision for a universe capable of forming stars and planets and chemistry and eventually life, might be explained. Black holes that produce stable, long-lived universes capable of forming more stars and more black holes would be more likely to reproduce. Universes whose constants allow complex structure would be overrepresented in the population of universes because they would produce the most black holes and therefore the most offspring universes. This is a form of cosmological natural selection. The universe we observe, fine-tuned for complexity and life, is fine-tuned because it is the descendant of universes that were successful at reproducing. This idea was first developed seriously by physicist Lee Smolin in the 1990s. It remains speculative, and it is not falsifiable in the same way that predictions of lambda CDM are falsifiable. But it is logically coherent, physically motivated, and it connects the fine-tuning problem, one of the deepest puzzles in fundamental physics, to the black hole cosmology picture in a way that neither framework accomplishes alone. Whether or not this picture is correct, the observation that motivated this discussion, the systematic asymmetry in galactic rotation directions, is real, it is measured, and it is currently without a satisfying explanation in standard cosmology. MOMZ-14 existed during the epoch of Ryanization. This is not a coincidence of timing. It is central to understanding what makes the galaxy significant beyond its distance record. Ryanization was not an instantaneous event. It was a process, a messy, patchy, extended transformation of the universe from neutral to ionized hydrogen that unfolded over hundreds of millions of years. The first stars and galaxies produced ultraviolet radiation that ionized the hydrogen gas immediately surrounding them, creating bubbles of transparent space in a universe that was otherwise still opaque to ultraviolet light. Those bubbles grew as more stars formed. They merged as neighboring star-forming regions expanded their influence. Eventually, after perhaps 700 to 800 million years of progressive ionization, the last pockets of neutral hydrogen were cleared and the universe became fully transparent to ultraviolet radiation for the first time since the Big Bang. At Z equals 14.44, 280 million years after the Big Bang, the universe was deep in the epoch of reionization. The process was just beginning. The neutral hydrogen fog was still mostly intact, except around the earliest, most energetic star-forming regions. MOMZ-14 was one of those regions, a bright source of ultraviolet radiation burning in the dark, carving out a bubble of ionized space around itself, contributing to the gradual clearing of the cosmic fog that would eventually render the universe transparent. When MOMZ-14's light was emitted, the universe around it was still mostly opaque at ultraviolet wavelengths. That is why the galaxy's shorter wavelength light, the ultraviolet that was produced by its hottest young stars, was absorbed before it could escape. The Lyman break that JWST detected in MOMZ-14's spectrum, the sharp cutoff where short wavelength light ends, is not just a feature of the galaxy's own gas, and it is a record of the neutral hydrogen fog that surrounded it. The universe itself is writing its own opacity into the spectrum of the galaxy. This makes MOMZ-14 not just a distance record, but a probe of the epoch of reionization. The details of its spectrum, beyond just the redshift measurement, carry information about the state of the intergalactic medium at 280 million years after the Big Bang. How much neutral hydrogen was surrounding it, how large the ionized bubble it had carved was, how efficiently it was converting stellar energy into ionizing radiation. At the moment MOMZ-14 was blazing, it was doing something that was, in a real physical sense, making the universe safe for the future. The ultraviolet radiation from galaxies like MOMZ-14 is what ultimately ended the cosmic dark ages. Without the ionizing radiation of these early star-forming systems, the universe might have remained opaque indefinitely. The transparency that allowed every subsequent generation of stars and galaxies to exist, that allowed the light from Andromeda to reach human eyes, that made every observation in the history of astronomy possible, was won by the ultraviolet output of galaxies like this one, burning in the first few 100 million years. This is a humbling thought. When JWST detected the light from MOMZ-14, it was catching a glimpse of the process that made all subsequent observation possible. A galaxy that was itself contributing to the transparency of the universe, in an epoch so early that the universe was still mostly dark, still mostly neutral, still in the process of becoming the place where the rest of cosmic history could unfold. MOMZ-14 was found in data from Cosmos Webb, a wide-field survey that covered enormous amounts of sky at relatively modest depth for JWST. But But some of the most extreme early galaxy discoveries have come from a different technique entirely, one that uses the universe itself as a telescope. Gravitational lensing is the bending of light by mass, predicted by Einstein's general theory of relativity more than a century ago, and observed for the first time in 1919 during a solar eclipse. Massive objects, galaxies, clusters of galaxies, even dark matter halos, bend the path of light passing through the gravitational field they create. This bending can work as a lens. Then a galaxy cluster sitting between us and a more distant background galaxy can focus and amplify the background galaxy's light, making objects visible that would otherwise be completely undetectable. The amplification can be extraordinary. In favorable geometries, gravitational lenses can magnify background objects by factors of tens or even hundreds. For galaxies at the extreme distances JWST targets, that amplification is the difference between detection and invisibility. One of the most powerful natural lenses in the observable universe is a galaxy cluster called Able 2744, known to astronomers as Pandora's cluster. It is a merging system. Several massive galaxy clusters colliding and intertwining, their gas clouds slamming together at millions of miles per hour, hit their dark matter halos interpenetrating in a gravitational collision that has been ongoing for billions of years. The result is an object of almost unparalleled mass, concentrated in a relatively small region of sky. That mass makes it one of the most powerful natural magnifying glasses humanity has ever used. The Uncover survey targeted Pandora's cluster specifically because of what its gravity could do to light coming from behind it. The lensing from Pandora's cluster is not uniform. The multiple merging subclusters create overlapping zones of gravitational distortion, each one bending light from different directions and at different magnifications, essentially creating dozens of separate gravitational lenses stacked on top of each other. The Uncover team achieved observation depths that made galaxies from the universe's first few 100 million years visible in detail, that would have required a telescope with a primary mirror hundreds of meters across without the lensing amplification. Spectroscopic follow-up was obtained for nearly 700 objects within the survey area, ranging from galaxies at modest redshifts to objects at redshift 13, placing them in the universe's first few 100 million years. Some of the most distant objects in the Uncover sample were completely undetected in prior surveys, including observations made by the Hubble Space Telescope over multiple decades. They existed in deep data, invisible, waiting for an instrument sensitive enough and a natural lens powerful enough to bring them to the surface. Yet the extreme magnification available through Pandora's cluster also allowed something that flat field surveys cannot achieve: the resolution of internal structure in early galaxies. Not just detecting them as points of light, but seeing inside them. Measuring star formation rates in individual regions of a galaxy that existed when the universe was less than 5% of its current age. Seeing whether those galaxies had central concentrations or were more diffuse. Beginning to ask whether the structures forming in the first billion years resemble the structures visible today. In many cases, they do not. The early galaxies revealed through Pandora's cluster and other powerful lenses look different from the organized disks and ellipticals of the modern universe. They are more compact, more irregular, more densely packed with star formation. But they are not formless. They have structure, organization, signs of a physical coherence that goes beyond the simple random clumping the standard model predicts for early cosmic structures. And among all the objects detected through gravitational lensing at extreme distances, one stands out for what it may or may not be. In 2022, astronomers using the Hubble Space Telescope detected something in a galaxy called the Sunrise Arc. Not a galaxy, not a cluster of stars, a single point of light, individual and isolated against the arc of its lensed host galaxy. Its name, Earendel, comes from an Old English word meaning rising light. It was chosen deliberately because the object described arrived at human instruments after a journey of nearly 13 billion years. Earendel is located at a redshift of approximately 6.2. Its light left its source when the universe was less than 1 billion years old. Individual stars at that distance should be completely invisible to any telescope ever built. The nearest stars outside our galaxy are already at the edge of individual stellar resolution. For the most powerful, ground-based instruments. The idea of resolving a single star, billions of light years away, seemed physically impossible for most of the 20th century. What made Earendel visible was a coincidence of geometry so precise that scientists initially struggled to accept it. The sunrise arc is located behind a galaxy cluster that sits about 5.5 billion light-years from Earth. That cluster bends and amplifies light from the galaxy behind it. But at the moment astronomers observed Earendel, something extraordinary was happening. The star happened to be aligned almost exactly on the gravitational caustic of that cluster, the line of maximum magnification, the place where the lensing effect is strongest. At that alignment, the amplification of Earendel's light reached levels that made the observation possible. Estimates of the true magnification varied widely, but the enhancement was enormous, potentially tens of thousands of times. That amplification is what made a star from the first billion years of the universe detectable by instruments in orbit around a planet that did not yet exist when the star was shining. Follow-up observations with JWST measured the star's spectrum more precisely. What came back was not the clean signature of a single hot star. The data suggested something more complex, possibly a binary system. Two stars orbiting each other with temperatures ranging from roughly 9,000 to 34,000 Kelvin. The cooler of the two would be comparable to some of the most massive stellar objects known in the local universe. The hotter would be at the upper limit of stellar temperatures. For the moment of its discovery, Earendel held the title of the most distant individual stellar object ever resolved by human instruments. That title has since been surpassed by even more extreme objects. Then, in 2025, a challenge to everything the field had concluded about Earendel appeared in the Astrophysical Journal letters. Massimo Pasquale and colleagues at the University of California, Berkeley, published a detailed alternative interpretation. Their central claim was straightforward to state: what if Earendel is not a single star at all? The alternative they proposed was that the object is a compact ancient cluster of stars, specifically a metal-poor globular cluster progenitor, one of the dense, tightly bound collections of hundreds of thousands of stars that formed in the earliest galaxies, and whose descendants orbit the Milky Way today as the ancient globular clusters visible through any backyard telescope. The argument rested on several lines of evidence. The first involved metallicity, the abundance of elements heavier than hydrogen and helium detectable in the object's light. Earendel's spectral properties match the range expected for very metal-poor stellar populations, consistent with globular cluster progenitors from the early universe, but not, on its own, distinguishing between a single star and a dense cluster of them. The more pointed argument came from comparing Earendel to another source in the same lensed arc, a separate object whose angular size and brightness had already led researchers to identify it as a star cluster. Earendel, Pasquale's team argued, shares enough properties with that confirmed cluster in terms of its stellar surface density, its age estimates, and the behavior of its brightness across different wavelengths, that the simpler explanation is that both objects belong to the same category. The key word is simpler. The gravitational magnification that made Earendel visible is extreme, but extreme magnification also comes with large uncertainty in the exact amplification factor. If the true magnification is on the lower end of the estimated range, a single star would produce far too little light to account for what JWST detected. A compact cluster of 1 million or more stars, even at very low metallicity, would have no such problem. Scientists working on Earendel responded that the question remains unsettled. The magnification estimates carry enough uncertainty to allow for both interpretations, and other features of the data are easier to explain with a single stellar source. The debate continues, and the final answer requires additional observations not yet scheduled. What is certain regardless of the outcome is the window Earendel opens. Whether it is a single massive star or a compact precursor to the kind of globular clusters orbiting ancient galaxies today, it represents a measurement at a distance, and an epoch that would have seemed like science fiction 20 years ago. At the frontier of individual stellar detection has been pushed to a place in the universe where the very first stars were forming, and that connection, the possible link between Earendel's compact cluster nature and MOM-Z, 1,4's nitrogen to carbon ratio, and the cosmic gem's dense early clusters, is not accidental. It is a convergence. 3 independent observations pointing toward the same conclusion. Globular cluster formation began in the first few 100 million years of cosmic time. It would be easy, reading through this accumulation of anomalies, to conclude that the standard model of cosmology is simply wrong, that lambda CDM has failed, that decades of work need to be discarded, that we must start again from scratch. That conclusion would be premature, and it would be unfair to one of the most successful theoretical frameworks in the history of science. Lambda CDM correctly predicts the anisotropy spectrum of the cosmic microwave background, the detailed pattern of temperature fluctuations in the oldest light in the universe, with extraordinary precision. The agreement between lambda CDM predictions and CMB observations is one of the most accurate confirmations of any theory in all of physics. The model correctly predicts the large-scale structure of the universe, the distribution of galaxies and clusters at relatively nearby distances, the correlation functions of galaxy positions, the baryon acoustic oscillation scale, all with a precision that any competing model struggles to match. These are not trivial successes. So they represent the confirmed predictions of a framework built on basic physics and tested against billions of data points spanning the entire observable universe. A framework that fails to explain a few dozen extremely distant galaxies, but correctly predicts essentially everything else at every other scale, is not obviously broken. It is telling you that something specific is wrong with the way it handles a specific epoch. The specific epoch is the first few 100 million years. The specific failure is in the treatment of early star formation efficiency, early galaxy mass assembly, and early chemical enrichment. The model works extremely well from roughly 500 million years after the Big Bang onward. It is the period before that, the cosmic dawn, the epoch of the first stars and the first organized structures, where the predictions keep failing to match what JWST finds. This is actually informative. It tells theorists where to look, not the entire framework, but specifically the physics of the earliest epoch. The feedback-free star formation hypothesis is a targeted modification, not a wholesale replacement. The population 3 stellar mass function is a targeted modification. Even proposals about dark matter behavior in the early universe are modifications to specific aspects of the model rather than rejections of the whole. The most likely outcome of the JWST crisis, as the community is increasingly calling it, is not the demolition of lambda CDM, but a significant expansion of our understanding of the first few 100 million years of cosmic history. The model will survive. It will need surgery. And the surgery will be informed by the most extraordinary dataset in the history of observational cosmology, being collected right now by a golden mirror floating in permanent cold 1.5 million kilometers from Earth. There is precedent for this kind of productive crisis. In the 1990s, observations of distant supernovae suggested that the expansion of the universe was accelerating rather than decelerating. This was not predicted by the standard model of the time. It required the addition of dark energy, a new ingredient with strange properties, to make the model fit the data. The addition was conceptually significant, philosophically uncomfortable, and physically mysterious. It is still physically mysterious. No one knows what dark energy is, but it is now part of the standard model, accepted by essentially all cosmologists, because it is what the data required. JWST may be forcing a similar addition. Not dark energy, but a revision to the early universe's star formation physics. Perhaps the addition of a more efficient mode of early star formation, perhaps a modification to the properties of dark matter halos at early times, perhaps something conceptually new that has not yet been written down in any paper. Science under pressure looks like crisis. It feels like the ground shifting. The history of cosmology is full of such moments, and most of them, in retrospect, were not moments of failure. They were moments of growth. Painful, disorienting, productive growth. MOM-Z14 is one galaxy, the record at the edge of what human instruments can detect. But to understand its significance, it helps to know the backdrop against which it sits. Christopher Consolise's revised estimate of 2 trillion galaxies in the observable universe deserves its own moment of consideration. Not the number in the abstract, but what the number actually means. 2 trillion. The number is too large for intuition, too large for comparison. Every analogy breaks under it. But try this one. If you could visit 1 galaxy per second, traveling through the observable universe at the rate of a single galaxy per second without pause. It would take you 63,000 years to visit them all. Human civilization, from the first writing in ancient Sumeria to the present day, spans approximately 10,000 years. You would not finish the visit in the entire span of recorded human history. You would not be close to finishing. You would have visited roughly 1/6 of the galaxies by the time all of human history had elapsed from your starting point. And more than 90% of those 2 trillion galaxies have never been seen by any instrument built by any civilization on this planet. The Hubble Deep Field, which counted 10,000 galaxies in a tiny patch of sky and launched 2 decades of revised galaxy count estimates, was capturing only the brightest fraction of the galaxy population at its surveyed depths. The small, numerous, faint galaxies that dominated the early universe were below Hubble's detection threshold. They were there. They are there. They are just invisible to instruments built for visible wavelengths. JWST was designed to change that. The Cosmos Web Catalog, with its nearly 800,000 galaxies spanning most of cosmic history, is an early step in building the complete census. Extrapolate the galaxy density in the Cosmos Web field across the full sky, and you arrive at a number consistent with the 2 trillion estimate, which means the Cosmos Web mosaic. The image that contains nearly 800,000 galaxies represents roughly 1,000th of 1% of the total sky. It is a keyhole. Through that keyhole, humanity has now looked 13.5 billion years back in time and found Mom Z14 blazing in the cosmic dawn. Every galaxy in that mosaic is the past itself, arriving in the present in the form of photons. Scientists studying the data are reading a record unlike anything humans have ever had access to. The mosaic is not a photograph of space. It is a photograph of time, a temporal cross-section through the entire history of the observable universe. From relatively nearby galaxies, billions of years old, to Mom Z14, billions of years older still. And inside that history, something is hidden that no one fully expected to find in such abundance. Galaxies that should not exist at the times we find them. Chemistry that requires history the universe had not yet accumulated. Structures organized beyond what the available time should allow. The keyhole is open. The investigation is ongoing. And every month, new data from JWST arrives that makes the picture richer, more detailed, more surprising, and more demanding of explanation. If the black hole cosmology picture has any validity, if our universe was born from a collapsed region of a parent universe, if the Big Bang was a bounce rather than an explosion, then the anomalies JWST is finding in the early universe take on a different character. In the standard picture, the early universe began in a state of extreme uniformity, seeded with tiny quantum fluctuations, and structure grew from those seeds under the influence of gravity alone. The first billion years are, in this picture, the slow beginning of a long process. The first tentative structures in a universe that has billions of years ahead of it to organize. In the black hole cosmology picture, the early universe did not begin from nothing. It began from the collapsed remnant of a previous universe's matter. The initial conditions were not a smooth quantum vacuum, but the compressed, rotationally energized, informationally dense product of a black hole's formation. The physics of the bounce, the expansion from a torsion-stabilized core rather than a singularity, might impose different initial conditions on the structure of the new universe than the standard Big Bang picture assumes. Specifically, a universe born from a rotating black hole inherits angular momentum. That angular momentum would express itself at large scales as a preferred direction, a slight asymmetry in the way matter distributed and organized during the early epochs. And that asymmetry might make structure formation in the early universe more efficient than standard lambda CDM predicts. Not because the fundamental laws are different, but because the initial conditions are different. More coherent, more organized, more seeded with the angular momentum that can drive the collapse of gas clouds into stars. This is speculative. To be clear, this is speculative. The black hole cosmology framework is not part of mainstream physical cosmology. It makes predictions that are difficult to test, consequences that are hard to trace through the full complexity of cosmic evolution. and it requires modifications to general relativity in the extreme conditions inside a black hole that have not been observationally confirmed. But it is not scientifically empty. It is motivated by real physics. Torsion in Einstein-Cartan theory is a real mathematical structure. The bounce mechanism it implies at extreme densities is a real consequence of the torsion dynamics. The inheritance of angular momentum from a parent universe's black hole is a real geometric consequence of the black hole cosmology picture. And the predictions it makes, preferred direction in galactic rotation, enhanced early structure formation, and specific patterns in the initial conditions of the observable universe are in principle testable. MOMZ14 cannot on its own confirm the black hole cosmology picture. No single observation can. But the accumulation of early universe anomalies found by JWST, the excessive luminosity, the chemical maturity, the organized structure, the globular cluster precursors, the massive early clusters, all of these would be less surprising in a universe that began from richer initial conditions than the standard model assumes. The connection between MOMZ14's nitrogen anomaly, the galactic rotation asymmetry, and the black hole cosmology picture is not a proven link. It is a pattern of observations that a non-standard initial condition could explain. Whether that explanation is correct is a question that will require more data, more theoretical work, and probably instruments that do not yet exist. But the question is legitimate, and asking it is how science moves forward. There is a moment worth pausing inside, a thought experiment that, if you let it land fully, changes how you look at the night sky. The photon that James Webb detected and converted into data about MOMZ14 had a biography that spans essentially the entire history of the observable universe. It was born inside MOMZ14 280 million years after the Big Bang, emitted by a star in the process of nuclear fusion. A hydrogen nucleus fused with another hydrogen nucleus, releasing energy, and some of that energy took the form of a photon, a particle of light. It emerged from the stellar interior, traveled outward through the star's outer layers, escaped into the interstellar gas of MOMZ14, and then set off across the universe. When that photon left MOMZ14, our galaxy did not exist, our sun did not exist, Earth did not exist. The atoms that would eventually make up every person alive today were dispersed in the intergalactic gas of the early universe, not yet assembled into any star, not yet forged into any heavy element, not yet anything that could by any stretch of imagination lead to the specific chain of events that produced a species capable of building a telescope. And that photon just flew. For 13.5 billion years, it flew. It crossed the expanding space between galaxies. The space it crossed was not static. It was expanding underneath it, stretching the photon's wavelength as it traveled, shifting it from the ultraviolet range in which it was born toward the infrared in which it was detected. And by the time it arrived at JWST's mirror, it carried within it the record of its journey, the stretched wavelength that encoded the distance, the absorbed shorter wavelengths that encoded the neutral hydrogen fog it had passed through, the emission features that encoded the chemistry of the galaxy it had left behind. The mirror intercepted it. One hexagonal segment of JWST's golden primary mirror, at a temperature of -233 degrees Celsius, with a surface smooth to within a fraction of a wavelength of light, in the permanent shade of a tennis court-sized sunshield, 1.5 million kilometers from Earth, caught that photon and focused it onto a detector. The detector converted the photon into an electrical signal. The electrical signal was processed by onboard computers. The processed data was transmitted to Earth via radio waves. Scientists at the Space Telescope Science Institute received the data, ran it through calibration pipelines, and produced images and spectra that captured what the photon had to say. And what it had to say was extraordinary. A galaxy at Z equals 14.44. A galaxy too bright for its epoch, too chemically evolved for its age. A galaxy that, in the nitrogen to carbon ratio written into its spectrum, might be telling us that the oldest stellar structures in our own cosmic neighborhood began forming before the universe was 3% of its current age. The photon did not choose what it carried, it simply carried it. For 13.5 billion years, across an expanding universe, through the thin intergalactic medium, past the forming galaxies of the cosmic dawn, through the epoch of ionization, past the formation of the first quasars and the first galaxy clusters, past the assembly of the Milky Way, past the formation of our solar system, past the origin of life on Earth, past the emergence of intelligence, past everything, it flew. And then one morning in deep space, a golden mirror caught it. This is what the James Webb Space Telescope does. It catches the messages that the universe has been sending since the beginning of time. Messages that no human instrument had any way of receiving until now. MOMZ-14 exists in a universe with 2 trillion galaxies. Each one of those galaxies contains hundreds of billions of stars. The conservative estimate for the number of stars in the observable universe is 10 to the power of 24. A 1 followed by 24 zeros, 10 septillion. And that number exceeds the total count of grains of sand on every beach and desert on the entire surface of this planet by a factor of approximately 1 million. Current data from exoplanet surveys suggests that roughly 1 in 5 stars, similar to our Sun, hosts an approximately Earth-sized planet in a zone where liquid water could exist on the surface. Even applying a far more conservative estimate, 1 potentially habitable world for every 100 stars across the entire observable universe produces a number of candidate worlds that approaches 10 to the 22nd power. 20 trillion planets where the chemistry of life might in principle have found purchase. And yet, every galaxy JWST reveals is a candidate. The Cosmos Webb mosaic contains 800,000 galaxies, each containing hundreds of billions of stars, and many of those stars hosting planets. Every faint smear of light in that image represents a system of worlds as old or older than our own, built from the same physics, the same chemistry, the same raw materials that produced life here. The SETI searches that have been running since Frank Drake pointed an 85-foot dish at 2 nearby stars in 1960 have returned a single result: 0. Not 1 confirmed extraterrestrial transmission, not 1 technosignature, not 1 engineered signal. In 65 years of organized searching, with instruments of ever-increasing sensitivity, with algorithms of ever-increasing sophistication, with datasets measured in petabytes, the answer has not changed. 60 years of accumulated null results run through statistical models now constrain the number of detectable technological civilizations in the Milky Way to fewer than 1 to 5 per century. That is not a guess. That is what the data says. Every new galaxy JWST finds deepens this silence. Each one is another data point in a distribution that keeps pointing toward the same result. The universe is vast. It has been available for life for billions of years, and nothing has announced itself. The Fermi paradox, first articulated at a lunch table in Los Alamos in 1950, when Enrico Fermi asked his colleagues, "Where is everybody?" and nobody could answer, has not been resolved in the 76 years since. JWST has made it vastly more acute. The telescope confirms that the universe is ancient, vast, full of stars and planets, hospitable to chemistry, and entirely, stubbornly, bewilderingly silent. There are several frameworks for thinking about this silence, and none of them are comfortable to live inside. The first is the Great Filter. The concept, formalized by economist Robin Hanson in 1996, proposes that somewhere along the path from simple chemistry to interstellar civilization lies a barrier so difficult to cross that almost no species manages it. The math is straightforward. If the universe should be full of civilizations but is not, at least one of the steps in the chain, from life to intelligence to technology to interstellar expansion, must have a near zero pass rate. The critical question is where the filter sits. If it is behind us, in the improbable emergence of complex life, or the even more improbable jump from single-celled organisms to multicellular complexity, then we are rare. The silence is explained by the near impossibility of getting this far. That possibility, strange as it sounds, is optimistic. The hard part is over. If the filter is ahead, the implications reverse completely. It would mean that civilizations consistently reach a certain threshold of technological capability and then collapse before spreading beyond their home star system. Our current moment, with its accumulating risks and global stresses, would look less like a difficult phase and more like the place where the chain typically breaks. In 2024, Michael Garrett published a paper proposing that artificial intelligence is the great filter. His argument was built on a timeline. Earth's first radio transmission occurred in 1895. 127 years later, in 2022, generative artificial intelligence systems began operating at a level that surprised even their creators. The jump from first radio wave to sophisticated AI took just over a century. Garrett's model assumes that any technological civilization follows a similar trajectory, and his estimate for the window between developing AI and being destroyed or fundamentally altered by it is roughly 200 years. 200 years. Not thousands. Not millions. On a cosmic timeline of 13.8 billion years, a 200-year detection window is like trying to photograph a specific lightning bolt during a storm lasting 4 million years. In early 2026, a researcher proposed a different mechanism, one that does not require machines at all. And the filter in this model is a species intelligence itself. Once a civilization is smart enough to decouple reproduction from survival, fertility rates fall. South Korea's total fertility rate in 2024 was 0.72. Replacement is 2.1. Japan is at 1.2. Every industrialized nation on Earth has fallen below replacement. The mathematics of population collapse, once it begins, are difficult to reverse. Every government that has tried has failed. This model projects human population peaking around 2080 and then declining, potentially to functional extinction within a millennium. If this is universal, if every intelligent species that gains control over its own reproduction follows the same curve, it explains the silence without invoking catastrophe. No nuclear war, no asteroid, no machine uprising. Just a slow, quiet fade across every inhabited world in every galaxy. Mom Z14 blazed in the cosmic dawn. Somewhere in its 240 light-year span, stars were forming, dying, scattering chemistry into the surrounding gas. Whether any of those stars had planets, whether any of those planets produced life, whether any of that life eventually looked up and asked the same questions we are asking, whether it lasted long enough to answer those questions. These are things we cannot know. But the observation that humanity just built the instrument capable of detecting Mom Z14 and then used it to find the oldest galaxy ever confirmed, and that all of this happened inside the 200-year window that Garrett's model says is the total lifespan of a civilization's detectability, is a coincidence worth sitting with. The record will fall again. That is not speculation. That is what the data says. JWST is still collecting observations. Cosmos Webb still has data being processed. Follow-up programs targeting extreme redshift candidates are ongoing. The telescope's lifetime is estimated at a minimum of 10 years, possibly 20, limited primarily by the fuel reserves of its station-keeping thrusters. In the years remaining, it will look deeper, find fainter objects, confirm more extreme redshifts. The question is not whether something will be found at Z greater than 14.44. The question is what that object will look like, whether it will be more surprising than MOMZ14 or less, whether its chemistry will be even more anomalous or more in line with expectations, whether it will carry additional evidence for the globular cluster connection, the chemical enrichment problem, and the structured early universe that keeps defying prediction. Each new record holder in the distance race is not just a number. It is a physical object with properties that can be measured, analyzed, compared to theory, and used to test models of early cosmic evolution. The distance record is almost secondary to the science. What matters is the accumulating data set of early universe objects that JWST is building. Each one a data point constraining the models, each one adding to the picture of what the first few 100 million years of cosmic history actually look like. Several programs are specifically designed to maximize the yield of extreme redshift discoveries. The JWST Advanced Deep Extragalactic Survey, JADES, has targeted fields where Hubble's deepest observations already provided a foundation, allowing JWST to build on decades of prior imaging and spectroscopy with its vastly superior infrared sensitivity. Primer, SEERS, NG Deep. Each of these programs adds coverage, depth, and spectroscopic confirmation to the growing catalog of early universe objects. And behind JWST, the next generation of facilities is being planned and built. The Nancy Grace Roman Space Telescope, when it launches, will survey areas of sky hundreds of times larger than JWST's deepest fields, at sensitivity approaching JWST levels. It will not go as deep in any given patch of sky, but will capture the statistical distribution of early galaxies across enormous volumes, providing the population-level context that individual deep fields cannot supply. Ground-based extremely large telescopes. The Extremely Large Telescope in Chile, with its 39-meter primary mirror and the 30-meter telescope planned for Mauna Kea, will be capable of spectroscopic follow-up at sensitivities beyond JWST's capabilities at certain wavelengths, allowing the chemical and physical properties of JWST-discovered galaxies to be measured with unprecedented precision. The story of MOMZ-14 and what it means for our understanding of early cosmic structure formation will not be completed in any single observation, any single paper, or any single telescope generation. It is an investigation that will span decades. The questions it raises about feedback-free star formation, about population-3 stellar masses, about globular cluster formation timescales, about the validity of the standard model in the earliest epoch, will be answered piece by piece, one observation at a time, one spectroscopic confirmation at a time, one revised theoretical framework at a time. That is how science works. Not with sudden, complete revelations, but with the gradual accumulation of measurements that slowly force the theoretical framework into a new shape. There is a number worth sitting with. Not 2 trillion galaxies, not 280 million years, not z equals 14.44, a more local number, one that grounds the entire enterprise in something recognizable. One galaxy out of 2 trillion. That is our address. The Milky Way, a moderately large spiral galaxy roughly 100,000 light-years across, containing somewhere between 100 billion and 400 billion stars. One galaxy out of 2 trillion. A moderately sized house on a street with no end. Within the Milky Way, one ordinary star among those hundreds of billions. A yellow dwarf of moderate mass, roughly 4.5 billion years old, located about 2/3 of the way from the galactic center to the outer edge of one of the galaxy's spiral arms. Nothing remarkable about it by any astronomical standard. Around that star, one planet at the right distance, with the right atmospheric chemistry, with liquid water on its surface, with a stable geological history long enough for chemistry to become biology, with life that became complex, with complexity that became intelligence, with intelligence that became curiosity, with curiosity that built telescopes. This is the chain that led to JWST. This is the chain that made it possible for a species to stand in a room and look at data from a galaxy that existed when the universe was 2% of its current age and understand, even imperfectly, was what they were looking at. Think about what that means. A universe that has been running for 13.8 billion years, that contains 2 trillion galaxies, that is built on a scaffold of dark matter invisible to every instrument ever created, in which 95% of the total energy content is in forms we cannot detect or understand, in which the observable portion is itself only a fraction of a possibly infinite whole. This universe has, in one small corner of one modest galaxy, orbiting one unremarkable star, produced something capable of asking what it is. MOMZ-14 blazed 280 million years after the Big Bang and knew nothing of this. Its stars burned and exploded and scattered chemistry into the surrounding gas. Its light began its 13.5 billion year journey toward a planet that did not yet exist, toward a species that had not yet evolved, and toward a technology that would not be invented for billions of years. The photon did not know what waited at the end of its path, but something was waiting. Something built with extraordinary precision, launched with extraordinary care, operated with extraordinary skill, and used to ask the question that gave all of this meaning. What is out there? How did it begin? What are we? The telescope's name contains an answer of sorts. James Webb was the NASA administrator who championed the Apollo program that first carried human beings to the surface of another world. The telescope named for him carries the next generation of that impulse outward, not to the moon, but to the edge of observable time. And what it found at that edge is not emptiness, not a smooth, featureless past, not the barren, primitive cosmos that the models predicted. And it found Mom Z14, blazing, already complex, already chemically mature, already doing things that our best theories said it had no right to be doing, already, in its nitrogen signature, carrying the ghost of the globular clusters that would one day orbit our galaxy. The universe at its earliest observable moment is richer than we thought, more organized, more active, more surprising. The honest accounting of where we stand after all of this is more important than any individual dramatic claim. The evidence is clear on several points. Mom Z14 exists at Z equals 14.44. Its spectroscopic conformation is secure. Its light was emitted 280 million years after the Big Bang. That is the most distant confirmed galaxy in the observable universe as of the publication of this analysis. The previous record, JADES-GS-Z14-0 at Z equals 14.18, was held for less than a year before Mom Z14's confirmation. The distance record will fall again. The question is how far. The nitrogen to carbon ratio in Mom Z14 is anomalous. The chemical signature matches globular cluster precursors. If this measurement is confirmed in subsequent analysis and not revealed to be an artifact of the data reduction, it implies that globular cluster formation began within the first 300 million years of cosmic history. This would require a significant revision to models of early stellar structure formation. MOMZ14 is more luminous than Lambda CDM predicts for its epoch. The excess luminosity is real. The explanations proposed, feedback-free star formation, population 3 stellar populations, AGN contamination, reduced dust extinction, are all physically plausible but individually insufficient to fully account for the observations. Some combination of these effects is almost certainly operating, but the precise mixture is unknown. The pattern of overly luminous, overly massive, overly chemically evolved galaxies at high redshift is systematic. It is not limited to MOMZ14. More than 100 galaxies from the first 400 million years of cosmic history have been confirmed by JWST. They are, as a population, brighter and more massive than the standard model predicts. The discrepancy is statistically significant and has not diminished as the dataset grew. The evidence is less clear on other points. Whether the standard model requires minor modifications to early star formation physics or something more fundamental is not yet known. Most cosmologists lean toward the former. The data do not yet require the latter, though they are consistent with it. Whether the galactic rotation asymmetry is real, and whether it requires new physics to explain, remains contested. Multiple groups have reported evidence for it using different data sets and methods. Not all analyses agree in their details. The systematic uncertainties are not fully quantified. Whether the black hole cosmology picture is correct, whether our universe was born from the bounce of a parent universe's black hole, is not known and is not directly testable with current instruments. It is a physically motivated framework that could explain several anomalies simultaneously, but the connection between the theoretical framework and specific observational predictions remains underdeveloped. The most important caveat of all concerns, what we do not know that we do not know. Every revision to the theoretical framework in the history of cosmology has been preceded by a period in which the anomalies were visible, but their interpretation was unclear. The anomalies JWST is finding are visible. Their interpretation is unclear. The history of science suggests we should expect surprise. Not just revision of existing models, but the emergence of ideas we do not currently have. The Cosmos Web catalog is public. The raw JWST data is archived and available to researchers worldwide. The spectroscopic confirmations are published in peer-reviewed journals. The analysis continues. New papers appear monthly. The dataset grows with every JWST observation cycle. Yet the investigation of what MOMZ-14 means for our understanding of cosmic origins is ongoing. The answers are incomplete. The questions are growing. When James Webb's mirror caught the photon from MOMZ-14 and converted it into data, something happened that has no precedent in the 13.5 billion year biography of that photon. For 13.5 billion years, the photon carried information. It encoded in its wavelength the temperature of the star that produced it. It encoded in its absorption features the chemistry of the gas it had passed through. It encoded in its overall spectral shape the history of the galaxy it had escaped. It carried all of this information across an expanding universe through the thin intergalactic void, through the epoch of reionization, through the long cosmic Middle Age, and past the formation of our solar system and the emergence of life in the entire history of civilization, carrying it all, inert, untranslated, unseen. When JWST's detector converted it to an electrical signal, that changed. The information was no longer just carried, it was read. A team of human scientists sitting in front of computers on a planet orbiting a star that did not exist when the photon was born, looked at the data and understood. Not completely, not perfectly, but genuinely understood. The wavelength that encoded distance was translated into a distance, 13.5 billion light-years. The absorption features that encoded chemistry were identified and measured. Nitrogen, carbon, their ratio anomalous. The overall spectral shape that encoded the galaxy's physical properties was matched to theoretical models. And MOMZ-14 was not just detected, it was known. That transition from carrying to being known is the most astonishing fact in this entire story. The universe at 2% of its current age was, as far as we know, completely devoid of anything capable of understanding it. Photons flew in every direction. Chemistry happened at stellar scales. Stars formed and died and scattered their elements. Galaxies assembled. All of this happened, and none of it was observed by any conscious thing. It simply happened, indifferent to whether anything witnessed it. 13.5 billion years later, one small corner of one small galaxy around one ordinary star has produced something that looks back and says, "We see you, we measure you, we understand partially and imperfectly what you were and what you did and what your existence means for the history of the cosmos." Carl Sagan wrote in the 1970s that we are a way for the cosmos to know itself. He meant it as a philosophical statement about the relationship between consciousness and the universe that produced it. In the case of MOMZ-14, the statement is not philosophical. It is literal. The cosmos produced MOMZ-14 280 million years after the Big Bang, burning with improbable brightness in the cosmic dawn. The cosmos also produced, 13.5 billion years later, a species that built a telescope cold enough and large enough and sensitive enough to catch the photons MOMZ-14 sent. And that species looked at the data and said, this is a galaxy at Z equals 14.44, and its nitrogen to carbon ratio is anomalous. And that anomaly might mean that the oldest stellar structures in our galaxy began forming before we thought they did. And if that is true, then the timeline of cosmic evolution is different from what we built, and we need to understand why. That chain, from photon to knowledge, from MOMZ-14's stellar atmosphere to a human scientist's understanding, is the most extraordinary thing the James Webb Space Telescope has accomplished. Not the record, not the anomaly, the knowing. Stand outside on a clear night and look up. The darkness between the stars is not empty. It is full of galaxies, most of them invisible to human eyes, all of them receding from each other on a tide of expanding space. Behind every visible star are billions of unseen galaxies extending back through time to the cosmic dawn. And behind the cosmic dawn is the epoch of reionization, and behind that the cosmic dark ages, and before the dark ages the first few 100,000 years when the universe was a fog of plasma and radiation, and before that the Big Bang itself, or whatever preceded it, or whatever gave rise to the conditions that allowed the Big Bang to occur. MOMZ-14, is the furthest back we have ever seen, the most distant confirmed galaxy in the observable universe. A blazing, chemically anomalous, improbably luminous structure that existed 280 million years after everything began. Its existence raises troubling questions, not because it is isolated, not because it is unique, but because it is the most extreme representative of a pattern, a systematic pattern of early universe objects that are more than the standard model can explain. Objects that push the timeline of cosmic structure formation earlier and faster and more efficient than any framework built before JWST predicted. The troubling questions are not signs of failure. They are signs of a science working exactly as it should. When observations consistently violate predictions, the predictions must change. When the universe consistently shows you something other than what your best theory said you would find, the theory must change. The only alternative is to stop looking, and that is not an option that serious science has ever chosen. James Webb will keep looking. The record will fall again. The chemical anomalies will be measured with greater precision. The theoretical frameworks will adapt and grow and possibly be replaced by something more accurate and more complete. The investigation of the earliest universe, the cosmic dawn, the epoch when Z14 blazed in the dark, is the central scientific project of this generation of astronomers. What they find will change what we think we know. It will not tell us everything. Science never does. Every answer produces new questions, and the best questions are always the ones that take the longest to ask. But the window into the earliest observable moment of cosmic history is open for the first time. A telescope floating in permanent cold 1.5 million kilometers from Earth, with a mirror made of 18 gold-plated hexagonal segments cooled to 40 degrees above absolute zero, is catching light that has been traveling since the universe was 2% of its current age. The light is arriving, the questions are alive. We are the universe looking back at itself. And what we see, when we look back far enough, is that the universe was not a simple, slowly assembling place of gradually increasing complexity. It was, from the very beginning, doing things we did not predict, building structures we could not anticipate, enriching chemistry we had no mechanism to explain, blazing with a brightness that violates the models and demands a better answer. Z14 is that demand, encoded in photons, carried for 13.5 billion years, finally received. The answer is coming. We begin. The story of Z14 is not only a story about cosmology. It is a story about engineering, about what it takes, materially and intellectually, to build a machine capable of detecting a photon that has been traveling for 13.5 billion years. The James Webb Space Telescope was conceived in the late 1980s and early 1990s when it became clear that Hubble, despite its extraordinary success, was approaching the limits of what an optical space telescope could achieve for deep-field astronomy. The early universe, the epoch JWST, was ultimately designed to observe, emits light that has been so severely redshifted by the expansion of space that it falls outside the wavelength range Hubble's detectors can efficiently capture. To see galaxies at redshifts above about 8 or 9 with any sensitivity, you need an infrared telescope. A large one, a cold one, placed far enough from Earth that the planet's own infrared radiation does not contaminate every observation. The requirements that fell out of these basic constraints were daunting. The primary mirror had to be large, and larger than could be launched on any existing rocket in one piece. The decision was made to build a segmented mirror, 18 hexagonal segments of beryllium coated with gold, folded during launch and deployed in space. The total collecting area of the primary mirror is 25.4 square meters, 6.5 meters across at its widest, more than 6 times the collecting area of Hubble's primary mirror. The telescope had to be cold. Infrared detectors are blinded by thermal emission from anything warm, including the telescope itself. JWST's detectors operate at temperatures ranging from -233 Celsius for the near-infrared instruments to -266 Celsius, just 7 degrees above absolute zero for the mid-infrared instrument. To achieve these temperatures passively, without mechanical cooling for the near-infrared instruments, the telescope had to be placed in permanent shade. The sun shield, a 5-layer membrane the size of a tennis court, keeps the telescope in the shadow of the sun, Earth, and Moon simultaneously. This requires a specific orbital location, the second Lagrange point, L2, 1.5 million kilometers directly away from Earth on the side opposite the Sun. At L2, the gravitational pulls of the Earth and Sun combine with the centrifugal effect of the orbit to create a stable equilibrium point. An object placed there can maintain its position with minimal fuel expenditure. JWST orbits around the L2 point in a halo orbit, keeping the sun shield always between itself and all sources of warmth. The launch was on December 25, 2021, aboard an Ariane 5 rocket from the Guyana Space Center in French Guiana. The deployment sequence that followed was the most complex autonomous engineering process ever attempted for a scientific instrument. 344 distinct single-point failures, any one of which would have ended the mission. The mirror segments unfolded and locked into position. The sun shield membranes deployed and tensioned to specifications. The secondary mirror extended on its tripod support structure to the correct position. The instruments powered on and cooled to operating temperatures. In January 2022, first light. In July 2022, the first released science images. The first deep field image, released on July 12, 2022, was a 12.5-hour exposure of the galaxy cluster SMACS 0723. It showed thousands of galaxies and gravitational arcs and structures that Hubble-era imagery had never hinted at. His researchers at the Space Telescope Science Institute described the experience of seeing it as a kind of disorientation, not the expected satisfaction of a machine performing as designed. Something more unsettling. The image contained things that the people who built the telescope had not fully anticipated would be visible. That disorientation has not diminished. If anything, it has intensified as the dataset has grown. The near-infrared camera, an IR cam, is the primary imaging instrument for wide-field deep surveys. It can simultaneously image two non-overlapping fields of view, each 2.2 by 4.4 arc-minutes, in wavelengths from 0.6 to 5 microns. It has unprecedented sensitivity in the 1 to 5 micron range, exactly the wavelengths at which the most distant observable galaxies, those at Z greater than 8, emit their red-shifted light. The near-infrared spectrograph, NIR-SPEC, is the instrument that provided the spectroscopic confirmation of MOMZ-14's redshift. It can simultaneously observe spectra of up to 100 objects within a 3.4 by 3.6 arc-minute field of view, using micro-shutter arrays that open and close individual cells to emit light from pre-selected targets while blocking background light. The spectral coverage runs from 0.6 to 5.3 microns across multiple gratings and prisms. For a galaxy at Z equals 14.44, the Lyman break falls at approximately 1.5 microns, well within NIR-SPEC's sensitive range. The MIRI, mid-infrared instrument, extends JWST's sensitivity from 5 to 28 microns, allowing observations of the most heavily dust-obscured galaxies in the early universe and providing critical, long-wavelength photometric measurements that constrain the older stellar populations in high-redshift galaxies. The combination of these instruments, operating on a 6.5-meter mirror at cryogenic temperatures at L2, has produced an observatory capable of detecting objects with apparent magnitudes beyond 31. To put that sensitivity in context, a magnitude 31 object is approximately 10 billion times fainter than the faintest stars visible to the naked eye on a clear night. MOMZ-14, at its observed flux density, sits at the edge of what even JWST can detect in a reasonable integration time. Fainter objects, or objects at even higher redshifts, will require longer exposures, gravitational lensing amplification, or both. And the engineers who built JWST spent 25 years getting from concept to launch. The scientists who used it to find MOMZ-14 built on that foundation in the third year of science operations. The discovery is simultaneously the product of a generation's worth of engineering effort and a few months of systematic data analysis. Both parts of the chain matter equally. Without the telescope, there is no data. Without the analysis, there is no discovery. There is a version of this story that gets lost in the technical language. A version that does not require knowing what a redshift is, or what lambda CDM stands for, or what the difference between photometric and spectroscopic measurements means. That version goes like this. A very long time ago, longer than any human number system naturally accommodates, everything began. We do not know why it began or what preceded it, or whether the question of what preceded it even means anything. We know only that something changed from a state of extreme density and temperature to a state of expansion and cooling, and that from that change, over billions of years, everything that exists emerged. For the first few 100 million years of that expansion, there were no stars, just cooling gas, darkness. The universe was full of material but empty of light. Then, in pockets of gas denser than their surroundings, gravity won. Gas clouds collapsed. Nuclear fusion ignited. Stars were born. They were violent, brief, brilliant. They died in explosions that scattered their newly forged elements into the surrounding gas. From that enriched gas, more stars formed. And around some of those stars, planets formed. And on some of those planets, chemistry became biology. And in one case, in one galaxy among 2 trillion, biology became a species that looked up at the night sky and asked what it was looking at. That species built instruments. First simple ones, then more sophisticated ones, then extraordinary ones. And eventually it built a telescope that could be launched into space, cooled to within a few degrees of absolute zero, and pointed at the most distant visible objects in the observable universe. That telescope found MOMZ-14, a galaxy that existed 280 million years after everything began. A galaxy blazing with light that should not yet have been possible. A galaxy whose chemistry carries the signature of structures that, according to everything we thought we knew, should not have begun forming for billions of years yet. It's a galaxy that is challenging the best scientific framework we have built for understanding how the universe evolved from a hot, dense beginning into the complex, structured, galaxy-filled cosmos we observe today. The challenge is not a failure of science. It is science doing what it was designed to do. Building the most accurate possible picture of reality. Testing that picture against observations. Revising the picture when the observations require it. Building a better picture. Testing again. The current picture has a crack in it. The observations from the first 300 million years of cosmic history do not quite fit the framework. Something in the early universe was forming stars faster, building chemical complexity sooner, organizing structure more efficiently than the best models predicted. We do not yet know what that something was. We are looking. Every number that describes MOMZ-14, its redshift, its luminosity, its nitrogen to carbon ratio, its tiny 240 light-year diameter, abstracts something that was, in the moment of its light's emission, deeply physical. There were stars inside MOMZ-14, real stars. Individual objects generating nuclear fusion, fusing hydrogen nuclei into helium, releasing the binding energy of atomic nuclei as light and heat. Objects with temperatures and masses and luminosities and lifetimes. Objects that, in many cases, were far more massive than any star in our galaxy today. The very first stars in the observable universe. The population 3 objects that theorists have been modeling for decades, but that no telescope has yet directly observed, formed from gas of essentially pure hydrogen and helium. No carbon, no oxygen, no nitrogen. Yet no iron, none of the heavy elements that contaminate the gas clouds from which stars form in the modern universe. This extreme chemical simplicity changed everything about how those stars formed and what they became. Without heavy elements to radiate energy during collapse, the gas clouds that formed the first stars could not cool as efficiently. They could not fragment into as many pieces. They collected more mass before nuclear ignition. The result, according to theoretical models, was stars of extraordinary mass, hundreds to potentially thousands of times the mass of our sun. Objects so massive that their lifetimes were measured in millions of years rather than the billions of years that characterize less massive stars. When those first enormous stars died, they died explosively. Not just as ordinary supernovae, but potentially as pair instability supernovae, objects so massive that the gamma rays produced in their cores create electron-positron pairs, reducing the radiation pressure that supports them against gravity, causing catastrophic collapse followed by an explosion powerful enough to entirely disrupt the star with no remnant left behind. These explosions scattered the first heavy elements into the surrounding gas with unprecedented efficiency. One star's death could enrich an enormous volume of surrounding material. The first generation of heavy element enrichment was both rapid and extreme, and the second generation of stars, forming from that enriched gas, would have had access to more efficient cooling mechanisms, allowing them to fragment into smaller pieces and produce a more modern-looking stellar population alongside the remaining giants. MOMZ 14, at 280 million years after the Big Bang, is likely in a transition period. Its stars include some of the earliest generations, possibly with substantial population 3 fractions, alongside second-generation stars forming from the enriched ejecta of the first. The nitrogen-to-carbon ratio in its spectrum is the chemical record of that transition. The nitrogen enrichment requires stellar generations that have already cycled. The specific ratio pattern matching globular clusters suggests that the enrichment process was not random, but followed a specific pattern associated with the particular stellar population mix of massive, rapidly cycling stars. And we cannot directly observe any of those individual stars at Z equals 14.44. Even JWST cannot resolve individual stellar objects in a galaxy 13.5 billion light-years away without extraordinary gravitational lensing amplification. What we see from MOMZ 14 is the integrated light of all of its stars combined, like looking at a city from orbit and seeing only the total glow of all its lights without being able to distinguish individual street lamps. But the integrated light carries the history. The spectrum of MOMZ 14 is the sum of the spectra of every star inside it, weighted by their individual luminosities. The chemical features in that spectrum are the chemical records of every star that has ever lived and died inside MOMZ 14, every supernova that has ever enriched its gas. Every generation of star formation that has ever cycled in its short 280 million year history. And what that history says, in the language of nitrogen and carbon, is that MOMZ 14 was already old for its age, already mature, already carrying within it the chemical legacy of multiple stellar generations that had formed, lived, and died faster and more efficiently than anything we see in the modern universe. Those stars are all gone now, long dead before Earth existed. Their light scattered in every direction from MOMZ 14's location in the early universe has been traveling outward for 13.5 billion years and will continue traveling for billions more. The specific photons that carried MOMZ 14's light toward Earth arrived at JWST's mirror in April 2025. The photons traveling in other directions are still traveling now, and they will reach parts of the universe that do not yet contain anything capable of receiving them. They will travel in darkness forever, carrying a message from the universe's infancy that nothing will ever read. That is what it means for something to be 13.5 billion light-years away. Not just that it is distant, but that it is the past. That the light we receive is the only contact we will ever have with an object that no longer looks the way it appears, in a location that is now vastly further away, surrounded by a cosmic environment that has changed beyond recognition in the 13.5 billion years since the photons we are catching left home. MOMZ 14. Tonight is not what we saw. It is 13.5 billion years older. What it looks like now, whether it still exists in any recognizable form, and whether it merged with other galaxies and became something larger, whether its stars have mostly died and left it as a dead red fossil galaxy, or whether it kept forming stars and grew into something comparable to the Milky Way, we do not know. The light from MOMZ 14 as it exists tonight will not arrive for another 13.5 billion years. We are looking at a ghost. An extraordinarily precise, scientifically measurable ghost. the ghost of a galaxy that blazed in the cosmic dawn and helped make the universe what it is today. MOMSI 14 is a record. Records are broken. That is their nature. The most distant confirmed galaxy today will not be the most distant confirmed galaxy next year. JWST is still observing. The data is still arriving. The analysis pipelines are still running. Somewhere in the next year's worth of observations, in the next pass through the Cosmos Web Catalog, or the JADES data, or the Sears field, or a new survey program not yet public, there is a galaxy at Z equals 14.5 or 15 or higher, waiting to be identified, waiting for a spectroscopic follow-up to confirm its redshift, waiting to take over the title. That future galaxy will raise its own troubling questions. Its chemistry will be even more anomalous, or not at all. Its luminosity will be even more excessive, or will start to be explained by the refined theoretical frameworks that the next few years of work will produce. Each new record holder is not just a number. It is a physical object. A real place where real stars were burning in the real early universe, and its measured properties will tell us something specific about the conditions that existed at its epoch. And adding another data point to the growing picture of what the cosmic dawn actually looked like. The picture is incomplete. It will always be incomplete. That is not a failure. Completeness is not the goal of science. Understanding is the goal, and understanding grows, not evenly, not always forward. Sometimes what looks like progress reveals itself as a wrong turn. Sometimes what looks like a wrong turn reveals itself as the beginning of a shorter path to a deeper truth. The standard model of cosmology is not broken. It is under stress. The stress is productive. It is forcing the community to look more carefully at the assumptions embedded in models of early star formation, early galaxy assembly, early chemical enrichment. Those assumptions are being tested by the best data set ever collected for the purpose of testing them. Some will survive. Some will be revised. Some will be replaced by ideas that have not yet been written down. MOMSI 14 will not be forgotten when the record falls. It will be a waypoint on the map of the early universe. A confirmed data point at Z equals 14.44. A chemical anomaly with a measured nitrogen to carbon ratio. A luminosity puzzle with a range of proposed solutions. A galaxy that for a brief period was the farthest confirmed object in the observable universe. That is what it will be in the archive of human knowledge. A waypoint. An important one. And the fact that a team of scientists at MWT looked at archival data from a program that covered a patch of sky 3 times the width of the full moon, found an object that appeared in infrared and vanished at shorter wavelengths, pointed the most expensive scientific instrument ever built directly at it, waited for the spectrograph to disperse its light, and confirmed that the light had been traveling since the universe was 280 million years old. That fact is extraordinary, independent of the record. They were reading a message from the beginning of time. They understood what it said. That is the most human thing that has ever happened in the history of cosmology. And it happened in April 2025, in data, from a telescope launched on Christmas Day 2021, built by tens of thousands of engineers and scientists over 25 years, in service of a question humans have been asking in one form or another for as long as they have been capable of asking anything. What is out there? How did it begin? What are we? The investigation continues. The window is open. We are the universe looking back at itself.